చిత్తూరు వినబడుతుందా సార్ మా వాయిస్? సార్ వాయిస్ వినబడుతుందా సార్ చిత్తూరు?
Sir, NRC PVK Chittur responding, sir.
Thank you, sir. Thank you.
Okay, sir. Am I audible, sir? Sir, am I audible, sir?
Sir?
Am I audible, sir?
Yes, sir. Audible, sir.
Thank you, sir.
Laptop
Women Vishaka, please respond. Women Vishaka. Women Vishaka, respond. PUKN, please respond.
Yes, sir. It's audible, sir.
Sir, NRC BVN
Vishal, go and read it. Audible.
Sir, NRC BVN responding, sir.
Yes, yes.
Sir, am I audible, sir? Sir, am I audible, sir?
Sir, PUKN, మాట్లాడండి.
Sir, am I audible, sir? Sir, responding, sir.
Okay, okay, sir. Women Vishaka. Women Vishaka, please respond.
Yes, sir. It's audible, sir. No.
Sir, continue మాట్లాడండి.
Sir?
Sir, మీ voice clarity లేదు, sir.
Vishal, audible.
Economics literature.
Chitturu, please respond. NRC Chitturu, please respond. NRC Vizag, please respond.
Madam, NRC PVK responding, madam.
Ah, sir. Sir, just for checking.
Okay, thank you, madam.
Okay, sir.
Yes,
NRC Vizag, please respond.
Vishaka 2 minutes responding.
Ah, thank you, sir. Thank you.
మేడం ఈ రోజు బాగా వినిపిస్తున్నట్టుంది మీకు ఆడియో ప్రాబ్లం లేదనుకుంటా
సార్ ఎక్కడి నుండి మాట్లాడుతున్నారు? సార్ రాంబాబు సార్.
మేడం
ఇప్పుడు వినిపిస్తుంది సార్. చిత్తూరు రెస్పాండెడ్, వైజాగ్ ఆల్సో సార్.
ఈరోజు బాగానే ఉన్నట్టుంది.
ఈరోజు బాగానే ఉంది. రాజమండ్రి చూడాలి సార్. రాజమండ్రి కొంచెం ప్రాబ్లం.
అంటే ఒకసారి ఏమవుతుందంటే ఆడియో జాబ్స్ ఎక్కడో చోట చిన్న న్యూస్ కనెక్షన్స్ ఉండటం వల్ల
మీ వాయిస్ క్లియర్ గా లేదు.
నా వాయిస్ అంటే బ్లూటూత్ పెట్టి మాట్లాడుతున్నాం మేడం.
ఓకే ఓకే సార్. ఓకే.
అంటే మాకు ఇక్కడ 2 TOTs రన్ చేసుకోవాలి కదా, ఒకటే సిస్టమ్ నుంచి ఒక ల్యాప్టాప్ నుంచి.
ఓకే ఓకే సార్. ఓకే ఓకే సార్.
ఓకే మేడం.
Rajahmundry NRC, please respond. Rajahmundry NRC. Rajahmundry NRC, Nandyal NRC, Anantapur NRC, please respond. The session will start shortly. Madam is waiting. Please respond all NRCs. సార్ ఉన్న ఎన్ఆర్సీస్ ఒకసారి వినండి. మనము మేడము ఏదైనా పీపీటీ ప్రజెంటేషన్ ఏదైనా ఉన్నప్పుడు మనం దాన్ని మ్యాక్సిమైజ్ చేసుకోవటము అవి ఒకసారి చూడండి. 200 పాయింట్స్ అంటే పర్సెంటేజ్ పెంచడం అట్లా ఏదైనా చేసినట్టయితే మ్యాక్సిమైజ్ అవుతుంది స్క్రీను. పార్టిసిపెంట్స్ చూడడానికి బాగుంటుంది సార్, కొంచెం అవి చూస్తూ ఉండండి. Good morning to our resource person, Indrani Chakravarti. Thank you, madam. Thank you for accepting our invitation and attending for this session. Thank you, madam. I request NRC Chitturu, please preside over this session.
A very good morning to all the participants from various NRCs throughout the state. So first of all, I would like to thank and pronounce to Professor Indrani Rai Chaudhary ma'am. She is previously she is a 10 days capacity building program, one of our coordinators in New Delhi, JNU New Delhi. So ma'am did MPhil from economics, Jadalpur University, and PhD Center for International Trade and Development, JNU. Previously she is worked as associate professor, Department of Economics, Jamia Millia Islamia, and one of the prestigious institutions in India, NIPFE, National Institute of Public Finance and Policy. So Finance Commission's writing, she is also one of the part of associate fellow. Then apart from that, ma'am has worked as associate fellow, Council for Social Development, New Delhi. So then madam's areas of interest are best peer reviewed publications. So many publications she has published. Her areas of madam's areas of interest is health economics, environmental economics. Apart from the development economics, applied game theory and quantitative methods. Ma'am, presently she is working as a professor of economics at one of the prestigious university in overall India, Jawaharlal Nehru University. Ma'am, this is a time for you to.
Thank you so much for this kind invitation. Am I audible? Hello, am I audible?
Yes, ma'am.
Yes, madam.
Okay. So thank you so much for the kind invitation, especially to Dr. Suba and all others who were also present in the JNU TOT workshop. And also, I would like to extend my heartfelt thanks to the Commissionerate of the College Education, Government of Andhra Pradesh, for taking this bold step of restructuring the syllabus and then re-energizing the faculties towards the advanced syllabus and taking the teachers who are present here, who are taking so much effort in understanding and restructuring the syllabus. So I would like to just, before I start, I would like to request you that this is a technical topic, so you may be some of the places you may not be very comfortable, or you may have some doubts. So in that case, please just intervene and ask questions. Otherwise, I would just run and it may not just serve your purpose. Second thing is that the topic is huge. So within 90 minutes, I don't know how much justice I will be able to do, but I'll try my best to make it simple, at the same time keeping the rigor of the topic and doing as much as possible. So thank you once again, and let me just share my slides. System is little different. I think. Can you see my slide? Hello?
Yes, madam. Yes.
Is the slide visible? Oh, thank
Yes,
you so
madam.
much.
Visible, madam.
So the topic, yes. So the topic which I am supposed to share today is the sampling distribution and probability distribution. And it is very much part of the the major part of the statistics is your inferential statistics, which deals with the estimation and hypothesis testing, which I'm supposed to do tomorrow. But before that, the background has to be set. So for that, the understanding of the probability distribution, the sampling distribution is important. Why the slides are not changing? Yes. Okay. So yes. So you all know the difference between the population and the sample. So population is something which is the entire set of the objects which you would like to study, but the sample is only a subset of the population. And this population is basically, given that it is huge, you need to just understand. In order to understand the population, there are some of the important numerical characteristics which can define population. They are called parameters, like population mean, population variance, population standard deviation. So they are basically population median. So they are called the parameters of the population. Why they are basically associated with the population, please remember. So when we call that parameters, that means they are basically characterizing the population. Similarly, but given that population is huge, so most of the time, given that time constraint, because of the time constraint or because of the monetary constraint, we cannot access the population entirely. So what we do, we study through the sample observation. So the sample is basically a small subset of the population. So we have to draw the sample in a very meticulous manner. That means designing of the sample is one challenge for the researcher. So why the designing is a challenge? Because we have to draw the sample from the population in such a way so that the sample bears the characteristics of the population. That means sample is a representative sample. That means it bears the characteristics of the population. Now, when parameter describes the population, there is another analogous concept which is called statistics. So statistics describe the sample. So when we say that the population mean, similarly there is a sample mean. So the sample mean is the statistics, population mean is the parameter. Okay, so in any textbook, if you consult, you will find that there is a conventionally some terms are basically used for the population and for the sample. Like the population is characterized by the population size is characterized by capital N, whereas small n stands for the sample. Mean, mu is the parameter for the population, which is the population mean, whereas x bar is the sample statistics or the sample mean. Similarly, sigma square is the population variance, S square is the sample variance. So all these mu, sigma square are the population parameter, whereas X bar, S square, these are the sample statistics. So I guess that you understand these concept. I'll now move to the next slide. So now we have, there are certain properties of the estimators. When we discuss, I think I can discuss this thing in the next, in the tomorrow's class, because there is not much time and it is little technical. But I would just like to tell you that suppose you have a random sample of size n, small n, drawn from a population of size capital N. So capital N, you may consider that the population size is say 1 lakh, and from that you draw a sample of say 500. Okay, so small n is 500, capital N is 1 lakh. Okay, now consider the sample variable cap x. X can be any variable of your choice which you want to study. So x assumes the value x1, x2, x3, xn. So these are the different values of the variable x, which you have drawn as a sample from the population. Okay. So the sample, these sample observations are having a sample mean, which is called x bar, which is nothing but, as you know, that's a summation of all these x1, x2, x3, xn divided by the sample size, which is small n. So summation xi divided by small n, where your I runs from 1 to n. Okay. So this is your x bar sample mean. Now, if you want to use these statistics to make inferences regarding the population mean, we need to know the distribution of x bar. So what is the distribution of x bar? Consider that the same sample size of small n is drawn from the same population of capital N, say k number of times, or say 100 number of times. Let me just make things much more simpler. Suppose your population size is 1000, okay, and your sample size is 100, right? So your small n is 100, capital N is your 1000. And this 100 sample you are drawing, say, for 50 times, right? So every time you are drawing this sample of 100 from the 1000 population size, you are noting the observations of x1, x2, x3, x100 and taking the mean of that, that particular draw. And you are repeating this drawing for, say, 100 times. And we are saying that we are drawing it with replacement. With replacement, without replacement, there are characteristics. I'm not going to all the technical details. For the time being, I'm saying that with replacement. That means once you study the samples, the observations of the 100 samples which you have drawn, again, you are returning it back to the population. And then next draw, again, you are drawing a sample of 100 and then study the observations of x1, x2, x3, xn and returning it back. So every time, 50 times, you are generating sample mean x bar. Okay. So this x bar, x1 bar, x2 bar, x3 bar, this way, x50 bar. So you have 50 sample mean, which are generated through 50 draws, okay, from the same population, and the sample size is also same, which is 100. Okay. Now, you have a population whose mean is, say, mu, which is your population parameter, right? And your intention is to know the, or to estimate that population mean mu, okay? But population is not accessible to you. You only have some control over the sample, a small subset of population. Now, from the sample observation, you would like to infer about the population mean mu, okay? So now, in order to do that, you are drawing sample of 100 and you are drawing it in such a manner, that means taking care of the design of the sample so that your sample is representative. But given that it is only 50 of 1000 observation, you cannot expect that all your x1 bar, x2 bar, x3 bar, x50 bar, all these sample statistics of sample mean are not equal to mu. They cannot be equal to mu, okay? They can be little more than mu, less than mu, but they are not supposed to be equal to mu. Now, if you take this mean of all these 50 means, what you get is basically, we call this that this must be equal to the mu, which is the population parameter or population mean. Okay, so this x1 bar, x2 bar, xn bar, all these sample means are not supposed to be different from each other entirely. They may follow that, some may be repeated because you are drawing from the same population of 1000, right? So in that case, some sample mean may be equal to the other draws, the sample mean of the other draws, but they follow certain distribution. The distribution of these sample statistics, here the sample mean, is called the sampling distribution or probability distribution. If you are not clear, this is little tricky. If you are not clear, please let me repeat. I don't mind repeating, but you just let me know that whether it is clear to all of you. Is it clear to all of you, or should I repeat? Hello? Hello? Am I audible?
Yes, ma'am. Yes, ma'am.
Am I audible?
Yes, madam.
Yes,
Ah,
ma'am,
so
it's audible.
is it clear to all of you?
Yes, madam.
Okay. Okay, thank you.
On just a noise reduction.
Little louder, voice is not very much audible. Hello?
Madam, it's clear only.
It is clear. Thank you so much. So what I am saying that every time you are drawing a sample mean, all the sample means say x1 bar, x2 bar, x3 bar, x50 bar are not supposed to be all equal. And they are also not supposed to be equal to the population parameter mu, which is the population mean. Okay. But all this sample mean follows a distribution. Okay. So this distribution is called the sampling distribution. Okay. You can calculate the sample, all these x1 bar, x2 bar, xn bar, x50 bar follows certain frequencies, and you can calculate the relative frequencies from them. These relative frequencies are nothing but the probabilities corresponding to the different x bar you get from the 50 draws of the sample of size 50. Okay. Okay, so now what I said that if you take the mean of all this mean, we call that this mean is called the expected value of x bar. And this expected value of x bar is supposed to be equal to mu, which is your population mean. And this property is called the unbiased properties. Okay, so this unbiased properties is one of the property of a good estimator. Now, there are other properties of the estimators, which I don't want to just do the details because they are more technical and it will take some time. If I find time tomorrow, then I will do some of these the properties which are related to unbiasedness, consistency property, efficiency properties, all these properties. Okay. So now we will go to the another concept, which is called the standard error of x bar. Okay. What is the standard error? Standard error is nothing but standard deviation of the sample. Okay. So standard deviation of the sample. So what is the efficacy of that? If your population observations are very apart from each other, they are dispersed. Okay. So in that case, the sample which you are drawing from the population are also supposed to be not very representative of the population because they are very dispersed from each other. Their deviation from the central value or the mean value is very high. So in that case, your sample standard deviation is also supposed to be very high. Okay. Now the sample standard deviation is called the standard error, and this is denoted by the formula sigma by under root n. What is sigma? If you recall, I said that sigma is the population standard deviation. And what is n? Small n is the sample size. Okay. Now we need to understand that what factors are going to influence the degree of dispersion of the sample mean around the population mean. Okay. So you can see that given that the standard error is basically equal to sigma by root over n, both sigma and the sample size are something which will influence the magnitude of standard error. And if your standard error is very high, you cannot expect that your sample mean is a good estimator of your population mean. Okay, because they are very much apart from each other. Okay, so the more widely, so now let us understand that what is the implication of high sample population standard deviation or population variance. That means sigmas. If your sigma is very high, that means in the population, the observations are very dispersed. Okay, so they are very much far apart from each other in terms of its central value, which is the mean. Okay, so in that case, obviously, given that your sigma is in the numerator, so it is obviously going to affect your standard error. Your standard error is also supposed to be very high. Okay, you don't want a high standard error because that will affect your estimation of the sample statistics for the population mean. Okay, so therefore you need to have a smaller. If your population standard deviation is small, your standard error is also small. How you can also reduce the standard error? By increasing the sample size. Why? Because n is in the denominator, you can see. So if you increase the sample size, what will happen? Your sample becomes more and more representative and your standard error is supposed to be lesser. Okay, but remember this n is in the denominator. So if your sample size is say 50, so obviously you will have a standard error sigma by under root 50. But if you double the sample size, say 100, what will happen? Something is inflating your denominator. So obviously your standard error will be less. If you make it 200, your standard error will be further reduced. Okay. So as you increase the sample size, your estimation will be more and more accurate. Your sample become more and more representative, and this will reduce your standard error. But please remember that there is an under root. So under root means that if your sample size are larger, definitely it reduces the probability of getting unrepresentative sample. But given that it is under root, it is subject to certain diminishing returns, in a sense that if you just double the sample size, suppose your sample size is basically say 100, if you double it to hundreds, or your sample size is say 25, and you just make it 4 times higher, that's 25 into 4. Okay, so how will be your standard error reduced? It is under root of 25 into 4, which is under root of 100, right? So which is basically meaning that how much will be reduced? 25, that means 5 into 2, 10. Is it clear? So only 10 times will be your standard error reduced, even though you are increasing, sorry, what I'm saying. It is if you are increasing your sample size is suppose 25, and you are increasing it 25 into 4 times. So what will be your standard implication for the standard error? Standard error is 25 under root of 25 into 4. So what does it mean? It is under root of 100. Under root of 100 means it is only 10. Okay. So that means you are not able to increase the standard error to the extent of 4 times. It is much lesser than that. Okay. So increasing the sample size is a good idea to reduce the standard error, but increasing the sample size is subject to diminishing returns in terms of increasing the precision of the estimator. Okay. Please do remember that. So for example, increasing the sample size by a factor 4 will reduce the standard error of X bar by only a factor of 2. Okay, so now we will come to the understanding of probability distribution. So what is a probability distribution? Suppose you have a random experiment which has some possible outcomes. Just consider the case of throwing a dice. When you throw a dice, what are the possible outcome? You can get 1, you can get 2, you can get 3, you can get 4, till 6. 1, 2, 3, 4, 5, 6. These are the possible outcome. You cannot get 100, or you cannot get 8, or you cannot get -5, right? So you are only supposed to get 1, 2, 3, 4, 5, 6 in that random experiment. Now, these 1, 2, 3, 4, 5, 6 definitely follows certain probabilities. What is that probability? It is, in this case, the probability is equal. That means 1 by 6, 1 by 6, 1 by 6 for all the 6 possible outcomes. Now, that means any random experiment is supposed to give some possible outcomes, and these possible outcomes, depending on the nature of the random experiments, can be discrete or continuous. What is a discrete random variable? Discrete random variable means it takes isolated value. What is a continuous random variable? It takes values within a certain interval. It can take infinite number of values. Okay, infinite number of values, like if you just measure the hemoglobin. Okay, so the hemoglobin of somebody is say 10.34, somebody is say 10.349, somebody is say 10.34999. So hemoglobin level of an individual can be within certain interval. That means it can be if it drops to at 3 or 2, I don't think that the person can survive. So there is a threshold between which your hemoglobin level should lie. 15 or 14 is very high, good hemoglobin, but say 3 or 2 is something which is very dangerous. So I think that person cannot survive with such a low hemoglobin. So there is an interval between which, or your person, if he has to survive, his hemoglobin may lie. It can be low, it can be high, but it cannot be. Have you heard that somebody's hemoglobin is at 100? It cannot be possible. So within this interval, depending upon how much precision you exercise in measuring the hemoglobin level in the blood, it depends upon that you can take the decimal value up to 8, up to 9. So you can have infinite values between these two thresholds of lower interval and upper interval. So we call these kinds of variable continuous variable. So the continuous variable, therefore, takes infinite number of values within a particular interval. Okay. Now, let us discuss what is so we have discussed two kinds of variable. One is discrete, another is a continuous. Now we will try to understand the probability distribution under the discrete random variable and under the continuous random variable. So under the discrete random variable, let us assume that the random variable capital X can have small n number of possible outcomes in a random experiment. Okay, so these are the x1, x2, x3, etc. So you can just the example which I have given, that if you throw a dice, you can have 6 possible outcomes, 1, 2, 3, 4, 5, 6. If you just toss a coin, you have 2 possible outcomes, the head or tail. So x is a random variable whose values are all discrete. Therefore, it is a discrete random variable which has these n number of possible outcomes, x1, x2, x3, etc. And with their probabilities p1, p2, p3, pn respectively. Okay. So now this specification of the set of the values of xi together with their probabilities pi, I runs from 1 to n, defines the probability distribution of x. So we call that fx, the small fx, is the probability distribution of the random variable x. If we say that this fx is basically equal to probability of x taking a certain value of say xi, here there is a typo, this is probability of x taking a value of xi. So, and this fx is called the probability mass function. So the probability distribution of a discrete random variable is called probability mass function, where this p is basically your probability. And you know that the probabilities cannot be negative and probability cannot exceed 1. So the pi, any probabilities you take, p1, p2, p3, pn, all these probabilities must lie within 0 and 1. So 0 probability Pi is equal to 0 means what? That impossible event. The event will not occur. Pi is equal to 1 means it's a sure or the certain event. So the Pi between 0 and 1, if you take, they are basically the true real probabilities, okay? And the sum of the probabilities, if x1, x2, xn, all these are exhaustive events, then in that case, they are all corresponding probabilities. If you take the sum, they must be equal to 1, okay? If you, these x1, x2, xn are not exhaustive. Like if I take the example of tossing the coin, throwing a dice, and if I consider the possible values of 1, 2, 3, 4, 5, not 6, I'm excluding 6. In that case, if you sum all the respective probabilities of 1, 2, 3, 4, 5, you are not supposed to get that their sum equal to 1. But when you are taking all possible outcome, that means all the outcomes are exhaustive. In that case, the sum of the respective probabilities is supposed to be equal to 1. Okay, is it clear? So this is the example which I said, that you have thrown a dice whose possible outcomes are 1, 2, 3, 4, 5, 6, and the probabilities are all 1 by 6, 1 by 6, 1 by 6. Okay. Now we will discuss the probability distribution function, which is for the continuous random variable. So as I already said, that if x is a continuous random variable, x can take its values within a 2 intervals. So you have to decide that what are the possible 2 values between which x can take the values. Okay. So in that case, let us consider that x has x is assuming its values within these 2 interval a and b. So a is less than equal to x, less than equal to b. Now, since a number of possible values of x is uncountably infinite, so as I already said that within these 2 thresholds, within this lower and the upper interval, x takes infinite number of values. Okay, so therefore, unlike in the discrete random probability distribution, we have assigned, you recall that we have taken x1, x2, x3, xn, because all these x1, x2, xn are discrete values of the random variable x. So our discrete outcome of the random variable of x, and we have assigned their corresponding probabilities p1, p2, p3, pn. Okay, but given that x here, x is a continuous random variable, we cannot do this. We cannot assign for every possible values of x their corresponding probabilities. Okay, therefore, in the case of the continuous probability distribution, we have to assign the probabilities within a kind of possible intervals of 2 numbers. Okay, so if I say that f(x) is a non-negative function means it cannot take any negative value. Okay, so non-negative function, then we say that suppose that probability x lying between c to d is, this sign is called the integration, c to d f(x) dx. So what does it mean? Just let me. So suppose I'm taking a distribution. Can you see the whiteboard?
Yes.
Oh.
Yes, ma'am.
So suppose this is your fx. Fx, where x is, we are measuring positive value of x here and say negative values of x here. And this is suppose your 0. I'm taking a symmetric distribution for the time being. So it can be asymmetric distribution as well. So this is, I'm claiming that this x is taking the values. X is a continuous random variable, and x takes the values within this interval of a and b. This is your a and this is your b. Okay. X is taking the values within this interval of a and b. So I am saying that x is taking the values within this interval of a and b, infinite number of values. But given that x, it cannot take any values beyond, say, minus a, or beyond this a, or beyond this plus a, beyond this b. So we can say that the probability of these probabilities of all the values between A to B is equal to 1. So probability of A less than equal to X less than equal to B must be equal to 1. Why? Because A and B are the two extreme thresholds between which all the values of X is supposed to lie. Therefore, A and B denotes the exhaustive set of values of X. Okay. Now, if I say that I'm interested to know what is the probability of X lying between C to D. Okay, C to D. Okay. So in that case, I'm interested. Suppose your C is somewhere here, C is somewhere here, and your D is somewhere here. So what I'm interested to know, I'm interested to know what is the probability of X lying between these two intervals. Okay, so I'm basically the probability is basically the area under this probability distribution Fx denoted by this shaded region. Okay, is it clear to all of you? Is it clear?
Yes,
So
madam.
in that case, it is basically denoted by a sign called integration sign. And the intervals are specified C to D, Fx, Tx. So once I'm writing C to D, F integration, Fx, Dx, I'm basically meaning I am interested in the area under the Fx curve within this interval of C to D. And once I'm writing this, it is evident that I am interested to know the probability within this C to D. If I'm saying that I'm interested to know what is the probability of X greater than equal to C. So in that case, I'm interested to know what is the probability, or this is your C, what is the probability of X taking any value either greater or equal to C. That means I'm interested to know the probability under this area of Fx, which is between the interval of C to B, which is basically integration C, B, B is the upper interval, C is the lower interval, Fx, dx. So this is basically the implication of writing integration. Is it clear to all of you? When I'm writing that X is a random variable, continuous random variable, which lies within the interval of A to B, it basically means that the integration A to B Fx dx must be equal to 1. Why? It is analogous to the, if you recall that in the discrete random variable, we have written summation pi is equal to 1. I runs from 1 to n. So what is this implies? That if the random variable is taking the possible outcomes of say x1, x2, x3, this way xn, corresponding probabilities are say p1, p2, p3, this way pn, then the probability, these x1, x2, xn are all exhaustive. So the sum of all these probabilities must be equal to 1. The same way here, given that the continuous random variables are always defined within a certain interval, so and we have this defined this x is a continuous random variable which takes its value within these two intervals of A and B. Therefore, integration of Fx dx, x lying between A to B must be equal to 1. This is analogous to the concept which we have described in the case of the discrete random variable of X. Is it clear to all of you? Is it clear?
Yes, madam.
If you have doubt, please do ask question, because it is to be gradually, the concept are to be given that it is a crash kind of a program, we cannot be too explicit and take a lot of time. So in that case, if you ask your doubt, that actually help me to be much more explicit and clarify some of the doubts. Okay, so please help yourself, otherwise it will be difficult for you and as well as me. I can't see your faces as well. Like in the proper physical classroom, we see the faces of the participants and the students, and then we try to just improvise our lecture or the delivery to just cater to the doubts of the students. Okay, so the facial expositions are completely missing, and that is basically a real difficulty so far as the technical deliveries are concerned in a online classroom. Okay, anyway, so if you have any doubt, please ask me. Otherwise, I will move to the next topic if there is any doubt. So what I'm trying to say is that in a continuous random variable, please remember that x takes values within certain interval, but x takes infinite number of values. And therefore, unlike in the discrete random variable, we cannot assign for each and every possible values of x, we cannot assign individual probabilities. So what we do, we basically assign the probabilities of x within certain intervals. Okay, so when we say that the probability x lying between C to D, it basically means that we are taking the area under the probability distribution, which is your fx, and it is denoted by the integration sign, integration C to D. C is the lower interval, D is the upper interval, fx dx. Okay, and the function fx is called the probability density function. So please do remember, when we are taking x as a continuous random variable, the probability distribution is called the probability density function, or PDF. But when we take x as a discrete random variable, the probability distribution is called PMF, probability mass function. So like the PMF, PDF also must satisfy two properties. That means if you claim fx is the PDF, fx must satisfies two properties. What are the two properties? That means that the probabilities cannot be negative. So fx must be greater than equal to 0. And the second property is that the fx dx, if you claim that all possible outcomes of x lies between the two interval a and b, in that case, integration a to b fx dx must be equal to 1, where your x is lying between the two possible range interval a and b. Is it clear?
Yes.
Is it clear? So things will be little more clear when we will describe the normal distribution, you know.
It's
But
clear,
for
madam.
the time being, it's clear. Thank you so much. Thank you. Okay. So now we were trying to understand another concept, which is called the cumulative distribution function, which is also called CDF. Okay. Cumulative distribution function, if you consult the book, you will find conventionally it is denoted by capital Fx. If you take any PMF or PDF, it is denoted by small fx. Okay, probability mass function and probability density functions are denoted by small fx, but cumulative distribution function is denoted by capital Fx. Okay, and this is basically means that the probability that a random variable takes a value less than or equal to a specified value of x, less than or equal to a specified value of x. That means if I write FC, F capital C, what does it mean? It means that I am basically trying to say the probability of x lying between this area. I'm basically interested to know x less than equal to c. X less than equal to c, given that x is lying between these two interval a and b. So I am basically interested to know, this one basically means probability x less than equal to c. And that actually means that I'm interested to know the area under fx within A to B, A to C, fx, dx. You understand now that this is basically this area which I am interested in. If I say that FD, what is FD? FD. FD is basically the entire area, this area. That means probability of X less than equal to D. Okay, probability of X less than equal to D means I'm interested to know what is the area under the fx within the interval of A and D. That means integration A D fx dx. Right? So which is basically the area under the curve fx within the interval of A and D. That means this area. Okay. So, but if I'm interested to know what is the area if greater than D? Okay. So what is the probability of X greater than equal to D? Okay. So in that case, I can take 1 minus probability of FD. Why? Because you know that the entire area under the fx is equal to 1 because it is a probability distribution. If you take the interval A to B, integration, that's the property, na? So if you take integration A to B, fx dx, this area must be equal to 1. So if you take the area, entire area 1 and deduct this area, so what you get is basically this area which you are interested in, a probability of X greater than equal to D. Is it clear to all of you? Okay. So in that sense, if I'm interested to know what is the probability of, I'll just go back here. What is the probability of X lying between C and D? I'm interested that what is the probability of X lying between C and D. That means I'm interested to know that probability of X C less than equal to X less than equal to D. Okay, so this is nothing but integration C to D fx dx. And in terms of cumulative distribution function, I can write capital FD minus capital FC. Why? Because what is capital FD? That is the cumulative distribution of FD, right? That means entire area of the X, fx and to the left of D. Okay? Is it clear? Entire area under the curve fx to the left of D, because FD is nothing but probability of X less than equal to D. Okay. So in that case, it is the entire area, this entire area to the left of D under the curve fx is your capital FD. Now, what is capital FC? Capital FC is basically the probability of X less than equal to C, right? Which is nothing but the entire area under the fx curve to the left of C. To the left of C means this to the left of this area. Okay. So if you deduct the entire this area from that, this area, what is left is this area which you are interested in. So probability of X lying between, that means probability of X lying between C and D is nothing but, in terms of the cumulative distribution function, capital FD minus capital FC. Is it clear? Is it clear to all of you?
Yes, madam.
Or should I repeat?
No, it's
No,
clear,
ma'am,
madam.
no need to repeat.
Clear? Okay. Okay. I'm now moving to the next concept. So another important property of the continuous, if X is a continuous random variable, is that X taking any discrete value is equal to 0. Okay. That means probability of X taking any discrete value is always equal to 0. Why it is so? You can just repeat this exercise by taking, so I am saying that what is the probability of x equal to c. Okay, so which is basically in terms of the cumulative distribution function, just the way we have done, we can write probability of x lying between the two intervals c and c, because I'm asking for the probability of x equal to c. It's a discrete value. Okay, so which is nothing but in terms of cumulative distribution function fc minus fc, which is equal to 0. So the probability of if x is a continuous random variable, probability of x taking any specific value is always equal to 0. Now, binomial and the Poisson I'm supposed to do, because this binomial in the what I planned is that we have now understood the two concepts. Sorry?
Can you show the previous slide, madam?
Yeah, this is the previous slide.
Area between the ordinates C and D minus. Can you explain that?
This is the one. This is the one. So if I say that what is the probability of say x lying between C and D, this is basically this area, right? So which is F capital FD minus capital FC. Same way, if I say what is the probability of x equal to C, okay, given that x is a continuous random variable, so if I say that it is basically capital FC minus capital FC, the same way we have defined for x lying between C to D, we say that FD minus FC. The same way, if I say that probability, just give me 1 minute. Probability of x equal to C is nothing but FC minus FC. Okay, so in that case, the probability of x equal to C becomes 0 if x is a continuous random variable. Okay, please do remember. Is it clear now? Is it clear?
Can you show the next slide, madam?
Next slide. This one.
Yeah. This one.
Yeah.
That is FC minus FD. We have written in the first
The
page.
one here we are trying to understand the probability of x lying between the two intervals C and D. Okay. Here we are trying to understand what is the probability of x equal to C, a discrete value. Here we are taking the probability within an interval of C and D. Here we are taking the probability of x equal to a discrete value of C. So in that case, just the same way I can write FC minus FC. So in that case, the probability comes out to be 0, which basically means if x is a continuous random variable, probability of any discrete value of x is always equal to 0. Is it clear?
Oh, okay, madam. Clear.
Okay. Now I am given that so far what the two concepts which I discussed, one is that the probability mass function when your x is a discrete random variable, the other is the probability density function when x is a continuous random variable. And what I planned is that I will do two probability distribution for the probability mass function, which are basically your binomial distribution and Poisson distribution. And for the probability density function, we are I'm planning to do normal distribution, standard normal distribution, and t distribution. Now, given that the normal distribution and the standard normal distribution is much more important, what I'll do, I'll come back here after doing normal and standard normal, because I'm not sure that how much time within 90 minutes I'll be able to cover. But I will be sharing this slide. So if I can't complete, in that case, you can always get back to me and I will definitely be happy to explain you. Okay, but let me first go to the normal distribution. So normal distribution, now we have done the probability density function, okay, PDF. Now from normal distribution, we will now understand how this concept is important, because in the probability theory, as you all know and agree, that the normal distribution is something which is very common. So whatever variable we try to address in the benchmark, we try to assume that the variable is a normal distribution, is following a normal distribution. Okay, so all your econometric exercise is majorly based on the assumption of normal distribution, and if there is a deviation from the normal distribution, what we found that the econometric exercises are very, very getting difficult and difficult. Okay, so but why the normal distribution is so popular? Because if you take any real life example of any variable, it is seen that the most of the variable in real world are either normally distributed or are approximately normally distributed. And the normal distribution, the concepts is useful because of the concept of central limit theorem. So what is central limit theorem? Tells you that when the number of observation is sufficiently large, that means if you are dealing with a large sample, the sampling distribution of sample mean, that means X bar, E of any random variable approximately converges to the normal distribution, irrespective of the shape of the population distribution. Under certain conditions, well, there are certain conditions, I'm not going to the details of that, but please do remember that it does, under the central limit theorem, it says that if you draw sample and then you continuous in a repeated sample, you derive the sample means for say finite number of repeated trials, then all this sample mean follows a distribution which is called sampling distribution, right? And this sampling distribution, if your sample size is pretty large, that means large sample, your sampling distribution must follow a normal distribution or approximately converges to the normal distribution, irrespective of the fact that whether the population distribution is normal or not. Okay. Now, this is basically the probability density function of the normal distribution, where we assume that your X is lying between two intervals. Here the intervals are -infinity and +infinity. So we are saying that within the interval of -infinity and +infinity, X can have all possible outcomes. And then the PDF or the probability density function of the normal distribution is basically defined by this. Even though it looks very difficult, but when you do in the real life, the estimations and other things, it is not, you don't have to be scared with this expression. Most importantly, you have to remember that the normal distribution is characterized by two parameters. What are these parameters? One is its mu, the second one is its variance. So whenever we write n mu sigma square, we basically know that it is a normal distribution, and here the mean is mu and the standard deviation is sigma square. That means these mu and sigma square are the parameters. Why? Because it characterizes the normal distribution. So once you know mu and sigma square, you actually know the unique shape of the particular normal distribution. Okay, so mu is the mean and of the population parameter and of the population, and sigma square is another parameter which is the variance. Okay, so these are the two parameters, please do remember, under the normal distribution. Now we have to understand various properties of the normal distribution. So what are the properties? The first important property is that it is symmetric around the mean value mu, which is the same time the mode and the median of the distribution. If a distribution is symmetric, you know that that is the characteristics that its mean is equal to median is equal to mode. Okay, so the mean, the central most value is the mean, and which is also by definition is the median, and it is also the mode. Why? Because it is a symmetric distribution. Now, what is the importance of the symmetric distribution? I'll show you the curve. So you can see that the central most value This is your x. You are measuring x in the horizontal axis, and this is your fx. That means the fx. That means the probability density function, or the PDF. Okay, and what you see that the central most value is the mean, which is also median, which is also mode. Why? Because if you take the ordinate values and just connect it here, this is the mode, right? This is why, because it has the maximum probability. Okay. And why it is symmetric? Because it divides, that mean is equal to x equal to mu. It divides the distribution into two equal parts. What does it mean? That this must be equal to this. What does it mean? That means given that normal distribution minus infinity to plus infinity, your x lies between minus infinity to plus infinity, your fx dx is equal to 1, which we have discussed in the last class, in the last slide. Okay, and given that the entire area under the normal distribution within plus minus infinity is equal to 1, and if you just take the ordinate value at x equal to mu, this part, the right hand side, this left hand side, the probability is 0, not this one, 0.5, and this one is also 0.5. Okay, that means 50% in the left hand side, 50% in the right hand side. It divides the distribution equally because it is a symmetric distribution. The two tails of the curve extends to infinity on the left hand side and right hand side. That means the two tails, it is minus infinity. You know that it in the left hand side it extends till minus infinity, in the right hand side plus infinity. The total area under the normal curve is equal to 1, which is 100%, which I've already said. It is an unimodal in the, that means the first derivative. So your calculus class is done. Is your calculus class is done? Done.
Not yet, madam, not yet.
Not yet. Okay. So, so in that case, I'll just abstain from saying. You can see that here the derivative is rising, here the derivative is falling. So I think I can abstain from saying that. But you will be able to understand these properties once you understand the derivatives and I think you will be able to understand. Okay, so it is unimodal. It is first order derivative is positive for x less than mu. That means here your derivative dy dx is positive, and here your dy dx is negative. What does it mean? As you increase, you know, these are all negative values. So as you increase your x value, if you increase your x value, you have to move this side. Okay. If you decrease your x value, you have to move this side. Why? Because these are all negative values. It in the to the left of these are all negative values. Okay, your derivative, your del dy by dx is positive, means what? It means that as you increase your x, your y increases. As you decrease your x, your y decreases. Okay, here your derivative is negative. Derivative negative means just the opposite, the inverse relationship between x and y. So if you increase your x, your y falls. That means your probabilities keeps on falling as you move to the left hand side. Is it clear? As you move to the right hand side, your x values increases. You are moving towards more and more towards plus infinity. Okay, so in that case, as you x increases, your fx, which is your probability, gradually falls. So your dy dx is negative here. Why it is negative here, and your dy dx is positive here. I'll just stop here because otherwise you don't understand the concept of the derivative. I'll keep on telling, you will feel bored. Okay, the next one is that it is having an inflection point. Inflection point basically means you have to take the second order derivative. Okay, so where at the first so what you find here, this is your mean value, and now if you take one standard deviation plus minus. So if you take plus one standard deviation from the mean value, it is mu plus sigma. If you take a 1 standard deviation away from the mean value in the negative side, that means mu minus sigma. And if you take minus 2 standard deviation away from the mean value, it is mu minus sigma in the left hand side, mu plus sigma in the right hand side. So what you are doing, you are allowing 1 standard deviation, 2 standard deviation, 3 standard deviation away from the mean value, both in the left hand side and in the right hand side. In the left hand side, when you are moving this side, you are actually reducing the value. That means mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. When you are moving this side in the right hand side, you are actually increasing the value. That means mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. That means the number of standard deviation away from the mean value. Now, if it is a symmetric curve, given that normal distribution is a symmetric curve, if you take the ordinate value of this, I can't have too much control on this whiteboard in this electronic platform because it gets fluctuated. But anyway, I guess that even my drawings are faulty, you'll be able to understand what I want to say. So it is basically saying that if it is a symmetric distribution, then the probability of this area, that means this area must be equal to the probability of this area, okay? And in the case of the normal distribution, it is roughly around 34%. That means 0.34 this side, 0.34 this side. What does it mean? It basically means integration mu plus sigma fx tx is basically 0.34, and this is exactly equal to integration mu minus sigma fx tx. Now you see, when you are taking the right hand side, the intervals are lower interval is mu, upper interval is mu plus sigma. So I am writing mu plus sigma fx dx. That means this is the area under the curve between the two ordinate value of mu and mu plus sigma. But when you are taking from the left hand side this area, so in that case your lower interval now is mu minus sigma. Please remember, because this is a smaller value as compared to mu, your upper interval is mu. So I am writing integration mu minus sigma mu fx dx. These two probabilities are equal because normal distribution is a symmetric distribution. That means the probability is 0.34. If you take 2 standard deviation, so your ordinate value is now this. Ordinate value is now this. So you are basically interested. So that means within plus minus 1 standard deviation, which is mu minus sigma, mu plus sigma, fx dx is basically probability of x less than equal to mu plus sigma, mu minus sigma, and this must be equal to 0.68, 68%, right? Understood? If you take the two ordinate value, that means plus minus 1 standard deviation from the mean value, the entire area is 68%. Is it clear? If you take plus minus 2 standard deviation, in that case, the entire area is around 95%. Entire area is around this area is, you can see that this area is 14%, and similarly this area should be also 14% because it is a symmetric distribution. You are here taking 2 standard deviation away from the mean value, mu minus 2 sigma, mu plus 2 sigma. Okay, so and if you add all, it comes roughly around 95%. Okay, but if you want to take the area between 1 standard deviation and 2 standard deviation, it is around 14%. Same is here. That means if you want to take the area between mu minus 1 sigma, mu minus 2 sigma, this is 14%. But if you take or mu plus minus 3 standard deviation, in that case, please do remember, so please do remember, sorry, please do remember that it is covering around 99.74% or 73%. Okay, so the within the plus minus 3 standard deviation. So just one. So it is saying that beyond the point x equal to mu minus 3 standard deviation and mu plus 3 standard deviation, the curve is close to the axis. That means the area under the curve beyond the 2 tail points in both the direction can be taken to 0. That means the 2 ends of the tail of the normal distribution extends towards plus infinity in the right hand side and minus infinity to the left hand side in the both the left hand side and the right hand side axis of the x-axis, but it doesn't touch. It is almost close to touching the x-axis, but it actually does not touch. This mathematical property is called asymptotes. Okay, so the asymptotic property, that means x is the fx is the 2 tails of the fx stretches towards minus infinity in the left hand side, plus infinity in the right hand side, with almost close to touching the x-axis, but not exactly touching. So we can say that beyond mu equal to x equal to mu minus 3 standard deviation or x equal to mu plus 3 standard deviation, the probability is almost equal to 0. Okay, so that's basically if you take beyond plus mu plus 3 standard deviation, this is almost touching the x-axis. Okay, asymptote towards x-axis. Similarly, left hand side is also the tail extreme ends is almost touching the x-axis. So beyond mu minus 3 standard deviation and beyond mu plus 3 standard deviation, the probability is almost equal to 0. Okay, so about 68% of the area lies under the curve within 1 standard deviation of the mean, which I've explained. About 95% of the area under the standard normal distribution lies within 2 standard deviation of the mean. Around 99.73 or 74% of the area lies under the curve within 3 standard deviation of the mean value, mu. Okay, I explained. Now we will discuss about the standard normal distribution. So standard normal distribution, mind it, is our important, is a special case of normal distribution. When you recall that the normal distribution is characterized by 2 parameters. One is mean, which is mu, another is a variance or standard deviation, which is sigma square or sigma, whichever you would like to say. Okay. Now, standard normal distribution is a special case of the normal distribution. Why? Because it has its 2 parameter, mu and sigma, which are equal to 0 and 1. So when you write in 0, 1, it basically means that you are representing a normal distribution which has a mean is equal to 0 and standard deviation is equal to 1. And this kind of normal distribution is called standard normal distribution. Okay, here also, but what is the difference between them? Like, as I said that in the normal distribution, x is a continuous random variable. X can take a value within plus infinity and minus infinity, right? Now, in the case of the for all possible values of x, if you take a transformation of x to z variant, okay? But what is z? Z is basically, you can see that z is here. You can see z is equal to x minus mu by sigma standard deviation. So if you take a transformation of all possible values of x, by taking this transformation z equal to x minus mu by sigma, you are actually transforming the fx into fz, which is a standard normal distribution, okay, where your z value now lies between minus infinity to plus infinity. Is it clear to all of you what I said? So N01, this one is N mu sigma, this one is N01, which is also a normal distribution, but it has a typical property of having 0 mean and 1 standard deviation. And this is basically drawn from this normal distribution by taking a transformation of z variant, which is x minus mu divided by standard deviation. Is it clear? Is it clear?
Yes, madam.
Yes, ma'am.
Thank you. Okay. Now, for the standard normal distribution, that like the normal distribution, we discussed the properties. The properties of the standard normal distributions is also same. Okay, the most of the properties are same. Only difference is that now it is a z variant which has its mean value equal to 0 and the standard deviation is equal to 1. Otherwise, it is the same symmetric bell-shaped curve which has its mean is equal to median is equal to mode, and the divides, that means at mean is equal to median is equal to mode. It divides the standard normal distribution into two equal parts where 50% lies in the left of the 0 and 50% lies in the right of the 0. Some important properties of the standard normal distribution you have to keep in mind. If and I think that these are very typical things when you will do the research and for basically understanding the z, t value and the p value. These are useful numbers. Okay, so the area under the standard normal distribution within plus minus 3 is, please remember, it is 99.73%. Area under the standard normal distribution within plus minus 2.58 is 99%. Area under the standard normal distribution within plus minus 1.96 is 95%. Okay, so if I just show you, this is a standard normal distribution. You are taking now z here, you are measuring z variable here instead of x. Okay, and here the z values lies between it. The standard normal distribution stretches towards plus infinity and minus infinity in the both sides of the tail, extends till like that. And what is important, 0 is now the mean value. Okay, 0 is the median, 0 is the mode. So it is the central most value having the highest probability. Now, if you take one standard deviation from the left hand deviation from both from the left hand side and the right hand side, what is the value now of z? It is your standard deviation. You remember that standard deviation is now equal to 1. So one standard deviation away from 0, which is the mean value, is plus 1 in the right hand side, minus 1 in the left hand side. Same way, if you take 2 standard deviation away from the mean value, it is plus 2 in the left hand right hand side, minus 2 in the left hand side, plus 3 in the right hand side. If you take 3 standard deviation, minus 3 in the left hand side. And if you recall that we said for the normal distribution, if you take plus minus 3 standard deviation away from the mean value, then the area under the probability distribution or PDF of fx is almost 1, which is 99.73. That means we said that probability of x lying between mu plus 3 standard deviation and mu minus 3 standard deviation is basically equal to 0.997 which means 99.73, 9973, 99 point. If you multiply it 100, you can say it is 99.73%. Okay, it is, that means almost all of the observation lies between these plus minus 3 standard deviation of the normal distribution. Okay, effects. But now you have a special case, which is a standard normal distribution. This is now your FZ. This is FZ. Your variate is now Z, which is you would have drawn by taking a transformation like this, x minus mu by sigma. Now, if you take plus minus 3 standard deviation from the mean value, you are basically taking any values of x lying between plus 3 and minus 3, okay? So which is basically must be equal to again 0.9973. Is it clear? Is it clear? That means within plus minus 3 of standard normal distribution of values of under the standard normal distribution, most of the observations are supposed to lie. Okay, so if it is like if you want to have within one standard deviation away from the mean value, what is the probability? Just like the one which you have done under the normal distribution, the probability under plus minus 1 standard deviation is 68%. Plus minus 2 standard deviation is 95%. Plus minus 3 standard deviation is 99.73%. Okay, that means within 0 to plus 1, the probability is around 34%. Same way, 0 to minus 1 probability is 34%. 1 to plus 2 probability is around 14%. Minus 1 to minus 2 is again probability is 14%. And this one you can just deduct from 99.73%. You will get the value. I can't remember exactly. So this area is 5%, 50%. This area is also 50%. So you can see that if you take plus minus 3, I discussed it in 99.73%. But if you take plus minus 2.58, the area under the standard normal distribution plus minus 2.58 is 99%. Plus minus 1.96 is 95%. Plus minus 3 is 99.73%. Okay, so this is more or less about the standard normal properties of the standard normal distribution. I will now help you to just do some calculations so that you will be understanding what you are doing. How much time I have? Can I take 5-10 minutes? Hello?
Yes,
Yes, ma'am. Yes, ma'am. You can take.
If you want to ask some questions, you can ask me, whatever, because the time is almost close. So whichever is preferable, I'll go by that. Hello? So what is the preference? If you want to ask some questions, in that case, I'll go by that. If you want me to continue to utilize the rest of the time, I can just help you to understand how to look at the table and then derive the probabilities under the normal distribution.
Yes,
Madam, good morning. Good morning, madam.
Huh?
Good morning, madam.
What should I do?
Madam, good morning, madam.
You please continue, ma'am. Continue.
Okay, good morning. Good morning. So then let us just, I have already shared the table. If you look at the table, now we will try to use the table to find out the values of the probabilities, okay? But just knowing those numbers actually is very helpful. That will help you to get the probabilities for many values of the standard normal variant. Now, if I take, say, consider the value of z equal to 2 in a standard normal distribution. So similarly, point z equal to minus 2 is also available. How you get a value of the probability lying between, so you are interested, suppose You are interested, suppose, to get the probability of Z lying between plus minus 2. Okay. So in that case, you have to go to the table. If you go to the table, go to the second page, okay, where you get all the class values, okay. If you take the 2, you are supposed to find out the 2. So on the first column, right, you can get a 2.0. Can you see 2.0 from the table? Hello? Can you see the 2.0 from the table?
Hello, madam.
Yes, right. 38.
2.0 from the table, can you see? The first column, just look at the page 2. Page 2.
Someone.
First column, or should I share?
Share it.
Okay, I'll share.
Madam,
Ah,
recapitulate, madam, once. Give a summary of it, madam, and share this PPT also, madam.
definitely I could
Okay.
share the PPT, but do you want me to recapitulate but not to go to the table?
Madam.
Okay, okay. So in that case, I'll just quickly tell you what we discussed in this session. We started with the definition of the parameter and then the statistics, and then we discussed about the standard error. We discussed about the sampling distribution or the probability distribution, and then we discussed about the two important properties of two important types of the probability distribution related to your X, if being a discrete random variable or a continuous random variable. If X is a discrete random variable, then the probability distribution or the sampling distribution is called the probability mass function. If X is a continuous random variable, then the probability distribution is called the probability density function. And we said that if Fx is a probability mass function, it must satisfy two properties. What are the two conditions or two assumptions? One is that your Fx should be greater than equal to 0. Rather, your Fx must lie between 0 and 1. Why? Because Fx is a probability. Fx cannot be negative. Fx cannot exceed 1. Okay. Another property is that summation of Fx is basically equal to 1. That means summation of all P1, P2, because X is a discrete random variable, summation of PIs. PIs are all probabilities of all the possible outcomes of Xi. Okay. So that means if X has n number of possible outcomes, X1, X2, X3, Xn, corresponding probabilities are say P1, P2, P3, Pn, then excuse me. Then summation Pi, if you take all possible values of Xi's, which are exhaustive, in that case, summation Pi must be equal to 1. Take X as a continuous random variable, then the properties, the same properties must be exercised. But instead of, excuse me, just let me take something. So instead of X, if X is a continuous random variable, we know that X takes the values. X cannot take any discrete values. That means X takes values within certain intervals. Suppose X takes the values within A and B. In that case, the all possible probability, you cannot assign probabilities to each and every possible values of X. Why? Because X is a continuous random variable, means that within a stipulated interval, X can take infinite number of values. So how you represent the probabilities? If you are interested to know, suppose the probabilities of X lying between say two intervals C and D. So it is basically denoted by integration C to D fx dx. What does it mean? That within the distribution of fx, you take the area under the, excuse me, you take the area under the coordinate value of C and D. That area is the probability of X lying between C and D. We also introduced another concept which is called the cumulative distribution function. What is cumulative distribution function? It basically takes for any values of X, the probability of X, say, less than equal to certain values, say C. So probability of X less than equal to C is actually denoted by capital FC. So when you write capital FC, it basically means that you are representing a probability of X less than equal to C. So after that, what we have done, we have actually described two probability distribution when your X is a continuous random variable. This two probability distributions are normal distribution and standard normal distribution. We discussed the properties of the normal distribution as well as the properties of the standard normal distribution. I think I have done this much within this interval. So if you have some queries, I'm really sorry I could not do the table part, and some little bit of calculations will have actually help you to understand the concept, the theoretical concept. But this is because of the lack of time I could not do. If you are interested, I can take one class after this workshop is over. That is just from my side. It has nothing, no formalities is required to actually help you with these concepts. Because within 90 minutes, it is very difficult to complete the topic, you know, because it's too big, too detailed. So much details are actually missed out. Yeah, any questions? In that case, I can take some questions.
Thank you so much, madam, for your initiative for taking one more class. Thank you. Hello.
Hello.
Madam, am I audible?
Yes, you are audible.
Yeah, nice to see you, madam, on the platform.
Nice to see you. Nice to see you. Why I'm not able to maximize it, I don't know. Anyway, so in that case, if I'm assuming that whatever is delivered, you understood. If there is any confusion or doubt, I can address that in tomorrow's class. Okay?
Okay.
Thank you.
Ma'am, a very good morning to.
I'm not able to hear.
Video on.
Yeah.
Please on.
Am I audible, ma'am?
Yes.
So, Professor Indrani Rai Chaudhary, ma'am, a well-known female economist in India, Center for the Study of Regional Development. Professor Indrani, ma'am, discussed elaborately population and sample mean standard error of X bar. Ma'am, explaining her lecture on probability distribution, random variable can be discrete or continuous. Ma'am touched apart from that continuous probability distribution, relative distribution. With the help of diagrammatical representation, normal distribution, standard normal distribution, and ends with Z value or Z score, properties of estimated sample mean. Ma'am, really, participate in every NRC throughout the state, gained some more knowledge after listening your lecture. Thank you, ma'am, for your valuable inputs with regard to probability distribution. Last but not least, I would like to add one more point about you, ma'am. the way you teach, the way you explain, the method, manner, and matter is exclusively fine unto the audience. Ma'am, on behalf of all the participants from economics family throughout the state, thank you for your wonderful lecture, ma'am. Thank you, ma'am.
I'm really humbled. Thank you so much. But you know, I am always feeling very uncomfortable because I am always scared that how much I'm able to deliver properly because online things, there are a lot of, you know, constraints. You cannot reach the audience properly. But anyway, I tried my best. Had it been in the offline mode, I would have explained things much better way. That is for sure. Okay, thank you.
Thank you, ma'am.
Thank you, madam. It's a great lecture. Thank you for sparing your valuable time for us. Thank you, madam.
Thank you so much. Thank you so much. Should I leave now?
Yes, ma'am. Yes. Yes, ma'am.
All the NRCs be back by 1:55 p.m.
అందుకని నిన్న ఉండిపోయినా సార్ సార్ రూమ్ లో సార్ రిక్వెస్ట్ చేసుకొని సార్ ఫిజిక్స్ లెక్చర్
Hello, good afternoon. Hi, hello, Arvind. Can you hear me? I
Sir.
can't hear you.
Yes, sir. Sir, very good afternoon, sir.
Can you hear me now?
Yes, sir. Yes, sir. I can clearly hear you, sir. We will
Okay,
start
okay,
the
all right.
session at 2 o'clock, sir.
Okay, okay. So meanwhile, let me just do something because I have joined from two different devices. So let me just share my screen.
Okay, sir. Yes, sir. It's visible.
Just a second. Is my screen visible?
Yes, sir. Yes, sir. It is very much
Okay,
visible.
all right, all right. Yeah.
We'll start at 2, sir.
Sure, sure, sure. I'm just checking it whether everything is working or not because that's important.
Oh, yes, sir. Sir, I think we can start.
Okay, okay, all right.
Very good afternoon, everyone. This is Samuel Arvind, lecturer in economics, Government Degree College, Satyaledu. Today, we have in our midst Dr. Sandeep Datta, assistant professor in economics from Delhi School of Economics. Dr. Sandeep Datta did his master's from JNU with distinct merit means scholarship, and he did his PhD from IIT Delhi with graduate assistantship. He had earlier worked as consultant to Department of Industrial Policy and Promotion, Ministry of Commerce and Industry, Government of India. Sir, thank you very much, sir, for being with us to deliver your lecture on unconstrained and constrained optimization. I have to tell everyone that when we approached Dr. Sandeep Datta, he was he was very much busy attending to his father, and we had requested him to make time for this. And despite his busy schedule and other things, he is giving his time for us, valuable time for us. Thank you very much, sir. You may take over, sir.
Okay. Thank you, Arvind, for this generous introduction, and thank you for inviting me in this lecture series. When I must say, when Arvind initially approached me, then I was a bit hesitant about my availability because of health concern at my place, but somehow I'm managing it, and now I'm glad that I'm here. And hope we will have a kind of an engaging session today. And today, basically, Arvind requested me to kind of deliver a lecture on unconstrained and constrained optimization for around 1.5 hours. And also the speaker special request, and then trying to keep it simple, because the thing is, the kind of thing we teach at Delhi School of Economics things a bit advanced. So, but I will try to keep things as simple as possible, so that at least at the end of the this lecture, at least we all have some sort of takeaways from this 1.5 hour lecture. So and if I go a bit fast, you can stop me at any time. So if you are having problem or issues in understanding some of the concepts, you can stop me at any point of time. And also, I must say, since this is 1.5 hours of lecture, so I won't be able to cover the theoretical aspect of the entire thing, because for that we need more number of lectures. So I will just mention some of the things, and also tell you the recommended texts or book. You can always go back and check it if needed. All right. So without any sort of list, I think we can begin. If you have any question, you can ask me at this stage, or I can take question in between or at the end of the presentation. Okay. Okay. All right. So before I kind of begin with this constraint optimization and unconstrained optimization, I then first we need to know the what is optimizations, right? So optimization is there in the name itself, optimization. I'm trying to basically we're trying to find the best possible solutions. Okay, we let's say, for example, we are trying to find out a solution from the there are multiple solutions of it, but we are trying to figure out what is the best solution, right? Sometimes many of you, like while teaching economics, you have come across with the profit maximization. So you are calculating the quantity produced or quantity sold in the market, so that the firm's profit is maximized. Similarly, the cost minimizations, right? So how firms are minimizing their cost with respect to quantity produced, right? So these are the things we would probably some of you are familiar with, or maybe you'll be familiar eventually at the end of the presentation. If you have to put a kind of you have to so what's the definition of optimization? So the optimization is the process of systematically identifying the best possible solution set of solution from a given set of alternatives. Basically, we are trying to figure out this, right? So we'll try to figure out. We'll try to in the entire presentation. We'll try to figure out what the best possible solution. All right, with the goal of achieving the most favorable outcome according to the specific criteria of the objective, right? So these processes basically, when you optimize, what do you do? Either you maximize or minimize of an objective function. So what is objective function? So I'll come later in the in few slides. I'll come to the objective function. Okay, and sometimes we have limitations, right? Sometimes when we are optimizing something, we are minimizing or maximizing some functions, right? We may or may not have certain limitation or restriction. When we have the restriction, we'll call it the constraint optimization. When we do not have any sort of restriction, then we call it unconstrained optimization. Is there in the name, right? So optimization seeks to improve efficiency, performance, or effectiveness in a wide range of application across different fields. It's not only in economics. We'll see the presence of optimization. We'll see it everywhere, right? In mathematics, in economics, in engineering, computer science, operations research, and beyond. In many areas we can we can see the application or optimization in day-to-day life. Eventually, for example, when you are going to, for example, all of us go to the market, right, and try and buy some goods or the food items or something, and every single time we are optimizing it. Okay, even though we are not following all these mathematical notations and calculations and all, but in the back of our mind, we still optimize it. Okay, how much potato I should buy from the market, or how much banana I should buy from the market, right? So all the time we are kind of doing all sorts of calculation, because I know there is a budget in my pocket, because let's say I have 100 rupees in my pocket, and on the basis of that we are always trying to figure out how much potato I should buy and how much banana I should buy, right? It's not the case. We are doing all sorts of mathematical calculation. Eventually we will go to the market, but the fundamental idea is this, right? So we are trying to maximize our utility. So in case we are going to market and trying to buy something, all right. So that's the kind of thing we'll be covering in the entire presentation. Okay, now let's move to the unconstant optimization. So as I said, there are two types of optimization. One is constant and unconstant. When you have the limitations of something, while doing the optimization, then we call it constant optimization. And when we do not have any sort of limitation, then we call it unconstant optimization. So we'll begin with without limitation thing, which means when you do not have any sort of constant, or do not have restriction or the limitations. All right. So now let's just begin with the definition of the optimization. The unconstant optimization involves maximizing or minimizing functions. So remember that when I'm saying optimizing, so we are talking about the both. No,
Sir,
at the same time, you cannot do the both.
Sir,
Yes.
excuse me. Sir, can you mute one device?
I think, just give me a second. I think I'm my one device, it is mute from where I'm sharing my screen, and I'm talking from other devices.
Yeah, okay. Sir.
Is it a problem?
Yes, sir, because on our side
Having echo?
Yes, sir.
So I think I have muted one device.
And speak from another one.
Is it okay now?
Yes, sir.
Arvind, is it okay?
Yes, sir. Yes, sir.
Okay. I'm so sorry, but I don't know. There may be a noise, background noise of fan, maybe. Otherwise, am I clear now? Am I audible now? Okay. All right. Yes. I can see your hand. Okay. All right. Okay, so I was talking about the unconstant optimization. Unconstant optimization involves maximizing or minimizing. When we are talking about the optimization, either I'm trying to find a maximum value or a minimum value. Okay, a function without any restriction or the constant. Okay, when you do not have any restriction, and also in economics, it is crucial to determine the optimal level of a variable to achieve a specific objective. And if we have to just pinpoint certain examples from economics, we can maximizing utility for the consumer. Probably all of you know it, because since you have been teaching economics for quite a long time, even some of you are more experienced than me. And also the maximizing profit of firms, minimizing cost of producer, optimizing of resource allocation in the market. There could be many more examples. Okay, maybe we also use in macroeconomics and all. Okay, so what's our objective? The objective is to find the optimal level of a variable without constant, thereby maximizing or minimizing an objective function. Now the question is, what is objective function? Okay, so objective function is objective function is there in the name. The function is represent a function to be optimized. Okay, I need to find out the maximum value or the minimum value of the function. Let's say, for example, if I draw this, let's say this is my x-axis, this is my y-axis. If I draw a curve, this, or maybe this, then I can see that this function takes the maximum value at over here. When let's say this is, let's say x is equal to 2 and minimum value of x is equal to 3, let's say. Okay, so this is my objective function, what, you know, the function to be optimized. Okay, and we sometimes denote it as f of x. Okay, first initially I'll discuss with the single variable optimization where I have only one choice variable. Okay, so initially I'll start with the single variable optimization. So I'm denoted by fx, and x is the decision variable. Okay, for example, sometimes you do the profit function, profit function, utility function, cost function. So you know all these things. If I take a cost function of 3x squared, let's say x is the quantity produced, or maybe about the input used, then let's say this is my cost function. If you just plot these things, it will somehow look like, I don't remember, maybe somewhere around this, I don't remember, so it's something like that. Okay, and my decision variable, so this is important, the x represented the quantity produced or sold or the input used. You can use in case of, let's say, input used. I can use it. So this x is my decision variable, how much quantity I should sell, or how much input I should use, or how much quantity I should produce. So this is my decision on which I am taking a decision. I have a profit function, let's say, or I have a cost function. I know if I produce this much, or maybe if I use this much input, my cost would be this. Let's say, if my inputs is, let's say, x2 unit, my cost would be 3x, x2 x squared minus 12x2 plus 10. So something like this, right? So my decision depends. So its name is there in the name, the decision variable on which I'm taking the decision. How much I need to produce, how much I need to sell, how much input I need to use, right? So that's why x is called the decision variable. Since I'm using the one variable thing, so I'm using the only fx. When you use the multiple variable, within an x1, x2, xn. So I can have many more decision variables. So if you have to take one example where I use more decision variables, for example, a firm is using 2 inputs for their production, okay, for the capital and the labor. In that case, let's see, if I have to write the cost function, I will let's say 3l squared plus 4k squared minus 12lk plus 10. Let's say something like this. So this is my cost function in case of 2 variables, right? It can be 2, 3, 4 till n, any finite number of variables I can have. But so now I'll discuss only, we'll focus only on one variable case. So these multivariable cases are complicated. We'll come later. Okay. All right. I hope this is clear. What is objective function and what is decision variable. Okay. And this is the fundamental thing of any sort of optimization. Whether you are doing for the constant optimization, unconstant optimization, constant optimization, equality or inequality, whatever you do, these fundamental things remain same. You have to figure out first what is the objective function and what are your decision variables, right? Okay, let's move on. Okay, now I'll just step by step I'll show then what is how to optimize a function. If I have an objective function, then how to optimize it, right? Let's say if I have a function like this, if you have to draw like this, let's say my function is this. Okay. So now my question is why the function takes a maximum value. So I can clearly see at this particular point, this function takes the maximum value, whatever let's say this is x prime, let's say. Here it takes the maximum value. Okay. So how do I get it? So now my question is, how do I get the x prime? From this particular figure, since I can draw the diagram, I can figure, okay, at the x prime, I can get the optimal value. But if it is something like this, yeah, many many ups and down, ups and down, ups and down. Okay, so it sometimes becomes difficult to figure out what's the optimum value or the maximum value or the minimum value every single time. Just looking graphically. Okay, so then it's better then we can use some a mathematical tool to figure out what's the optimum value or the optimum value, it is minimum value or the maximum value. Okay, so what's the step one? The step one is to identify the objective function. What is your objective function? Okay, objective function fx, for example, let's say cost minimization or the profit maximization. Okay, if I say that let's say my profit function is, let's say, pi x is equal to 12x minus 2x square. If this is my profit function, then this is my, so if I know my this much profit I will generate if I sell x unit of output in the market. But now the question is how much x I need to produce. Okay, so now, so first what I'll do, I'll figure out my objective function. Since this is a single variable case, I know my decision variable is the x. What is x? It is a quantity produced, for example. Okay, now let's move on to the next step. Step 2 is the first calculate the first derivative of the objective function f prime x with respect to the decision variables. I hope all of you know the how to calculate the derivative. I'm not going into that detail. So calculate the first derivative of the objective function f prime x with respect to the decision variable. Okay, since I have, let's say, pi x, so what I'll do according to this thing, the pi x, this is my, let's say, if I take the previous example, my 12x minus, let's say, 2x square. If this is my objective function, then I'll take the first derivative. So I'll take d pi dx, then d dx of 12x minus 2x square. So then is equal to 12 minus 4x. Okay, now set the derivative equal to 0 to find the critical point where the function may reach the maximum or the minimum or the saddle point. So what I'll do this d pi x dx is equal to 0, which implies 12x minus 4x, sorry, not 12x, 12 minus 4x is equal to 0, and I'll solve for x, that is the x star, that the critical value where the maximum, the function takes the optimum value. It could be minimum, it could be maximum. Whether it is minimum or maximum, for that we need to check further. So it is 12 upon 4 is 3, right? If I have to draw the curve, if we see that like this curve is something like this, and let's say this is 3. Okay, can anyone say that why do I make the first derivative this derivative equal to 0?
To find the derivative equal to 0, sir. Find out the critical points.
Yeah, that's the fundamental idea of finding the critical point. So why we are setting it to 0? Because at this point you see that slope of this curve becomes 0, right? As soon as this increases and start decreasing and becomes 0. So that's why or whether you take this curve, it happens the same over here. It becomes 0. So at the optimal point or the critical point, right? But this critical point, the slope is 0. Okay, so that's why we are setting it to equal to 0. It can be at this point, it can be at this point. In this case, it is maximum, in this case, it is the minimum. Or it is, but without drawing the curve, how would I know what is maximum or the minimum? But in order to know that whether this x prime x star is equal to 3, the function will take the maximum value. How would I know that? For that, we need to check further. Okay. Okay, so you will, so now when you set the value 0, solve the equation obtained in the step 2, find the critical points of x1 to xn. So there could be multiple critical points. Okay, for example, in that case, I have taken the, so for example, in this case, we have only one critical point, x star is equal to 3. Okay, if I take a different example, for example, let me say 12x² minus 4x cubed. If this is my objective function, okay, then how many critical point I can find? So let's say df by dx, it would be around 24, sorry, 24x minus 12x square is equal to 0. That means I just have x out, that x 2 minus x is equal to 0, which means I'm getting two critical points, that x1 is equal to 0 and x2 is equal to 2. Okay, so now I have two critical points, x1 equal to 0 and x2 is equal to 2. But does that mean that all the critical points, at all these critical points, I'll get the optimum value? Okay, its answer is may or may not be. Okay, so the critical point represents the potential solution of the optimization. So these critical points are the potential solution. These are not the solution. These are the potential solution. These are the potential solution of the optimization problem. Okay, now we'll just classify all these critical points. So far what we have done the step 1, defining the objective function and what is my choice variable, or okay, or the decision variable. Next step is to, once I have figured out this is my objective function and these are my choice variable, I'll take the first derivative with respect to the choice variable and set it equal to 0, and once I set it equal to 0, I'll find the set of critical points. Okay, let's say x1 to xn. But now how do I figure out whether which are those critical points which gives me the optimum value, right? So in order to understand that, we use the second derivative to classify the critical point as maxima or the minima or the saddle point. So what are these criteria? Evaluate the second order derivative f double prime x as the critical point. If f double prime x greater than 0 is the local minima. If f double prime x less than 0 is the local maxima, and if it is 0 is inconclusive. Okay, let's check. So
Sir, one small doubt, sir.
Yes.
Excuse me, sir.
Yes, go ahead. Yes, I can hear you. Please go ahead.
In the first order derivative, to find out the critical points, we are making it as f of x is equals to 0. In the first order derivative.
No. So first order, you calculate the f prime x and set it equal to 0, and from there you will find a list of solutions. You will find, let's say, x1, x2, x3, x4, and so on. You will find many critical points. So I'm taking a critical point 1 is equal to x, naming is a critical point 1 is equal to x1, x2, x3, x3. Then depending on what first order condition you receive. Okay.
No, my doubt is
clear?
in the first order. No, my doubt is in the first order derivative, we are making it is 0 to find out the critical points. Whereas in the second order derivative, if f of x is equals to 0, the test is inconclusive. Why is it so?
So for that, you have to explain the entire mathematical thing. Okay, when this f double prime x, and of course remember that then we are evaluating f second order derivative at each of the critical points. Okay, and you will see that when this is 0 and it is not. Okay, let's take the example which I have taken. The first example I have taken, the f of x was, if I can correctly remember, 12x minus, I think, 2x square, and we received x is equal to 3, x star is equal to 3. Okay, so my f prime x was 12 minus 4x, right? So what is f double prime x? What is it, f double prime x? Minus 4, right?
Minus 4.
Right, so it is less than 0. So we at my so anyway, whether putting x is equal to 2, because anyway this is exactly -4, so it doesn't, is independent of your decision variable, and it clearly shows that if double prime is less than 0 is a local maximum. And if you just plot it, then you see that x is equal to 2, that x tried is equal to 3, the function obtained the maximum value. Okay, now let's take this other example, 12x squared minus 4x cubed. So the other example was, let's say 12x squared minus 4x cubed. So what was my first order condition? This was 24x minus
12x squared. 12x squared.
12x squared. All right, thank you. And what is my f double prime x? It is 24 minus again 24x.
24x, 24x.
All right. So now I have to check. Now I have obtained how many critical points for this particular thing? X1 equal to 2 critical points, 0 and 2. For each of the critical point, I have to check the second order condition. When f double prime 0, it gives you 24, and f double prime 2, it gives you minus 24, right? Is it? Yes. So you see, this is greater than 0. This is less than 0. So this shows that x is equal to 0, the function takes the minimum value, right? According to this condition. And if x is equal to 2, then this f double prime x is minus 24, which is less than 0, which means it gives me the
That means one is minimum and
maximum
one is
value.
maximum. One is minimum and one is maximum.
Yes, but minimum is obtained at x is equal to 0, and maximum is obtained at x is equal to 2. Okay, so now you can see from the same function, it's not the case that we have one objective function, and either we have only maximum, only minima, but we still can have both in the same from the same function or same objective function can give me both maxima and the minima. Okay, all right. And why f double prime x is equal to 0, test is inconclusive. So I can leave it to you for your understanding. You can always go back. So I'm not going into the theoretical part of these things. Why f double prime x is equal to 0, test is inconclusive. So if you have idea about the second order derivative, because the first order derivative gives you the slope, and the second order derivative of this case, it gives you the rate of growth of slope. Okay, so you can easily show that, you can easily understand why when f double prime x greater than 0 gives you minima, and when f double prime x less than 0 gives you maxima, and when f double prime x is equal to 0, test is inconclusive. From that concept, you can easily understand. Okay, so I'm not going into the detail of this thing because I do not have enough time to do these things. I can recommend you some book. You can always go back and check.
Okay, thank you, thank you.
Okay, all right. Now next, am I going too slow? Because I have many things to cover. There are 60 slides. Okay, all right. Okay, all right. Let's take one example from the economics. Okay, I think many of you will be familiar with this sort of thing. A firm is confronted with the cost function px is equal to 3x squared minus 12x plus 10 when it representing the quantity produced, or I would say input used. I would say input used, and determine the input quantity that minimizes the cost of the firm. It's exactly the same thing. So what is my objective function? This is my objective function, because I am the farm. Let's say I'm the farm owner. I am fetching this cost function. Okay, this is my objective function. Then I have to figure out how much input will minimize my cost. Okay, so then what I'll do, again, I have defined my objective function, that is 3x squared minus 12x plus 10. In this case, it is defined, but in many economics problem, you'll see you'll be given with the inverse demand function and all these cost faced by the market. And there may be complex scenarios. I didn't go into that. I picked up the simple functional form from the I picked up a simple functional form but maybe you may have to construct this functional form from a from, let's say, there are some information is provided to you, and on the basis of this information you may have to construct this, let's say, this objective function. Here it is given. Okay, just for the sake of utilize the time, I have just use this kind of functional form. Now, how do I optimize it? So, or how do I minimize it? Then what I'll do first, the first step is that, no, take the first order derivative, like p prime x is equal to 6x minus 12, as you know. Now, what I'll do, I'll figure out the its critical point. What's my critical point? I'll set this is equal to 0. If I'm setting this is equal to 0, then I'm finding that x is equal to 2. This is simple math. Now, I don't know that x is equal to 2 is the max. At this particular point, arm will minimize or the maximize. Okay? Or nothing will happen. I don't know. But I need to check further whether the form will minimize the max. Then what I'll go for the second order derivative, the p double prime x. Okay? So, and then which gives you that 6, which is independent of x. Therefore, you don't need to evaluate it at 2. Therefore, p double prime x greater than 0, that we obtain a local minima. All right. So the firm minimizes the cost by selling or using 2 units of inputs in our farm. Okay. So these are the kind of example you can take. You can create your own example to understand the concept in detail. You can pick up any functional form, whichever you like, and then test it, whether it is inconclusive or not. Right? Let's see if I give just for your kind of understanding. Just check with this thing. Let's say 12 x cube minus 8 x to the power 4, and if fx is equal to this, just this you can just try. Once this lecture is over, you can try with this function, or when the function is optimized, at what value of x the function is optimized, the value of the function will take the optimal value, be it minimum or the maximum. Okay, so first again check the critical point, figure out the critical point, and once the critical points are achieved, take the second order derivative, and then plug in all these critical point and check whether the second order derivative is less than 0 or greater than 0 or equal to 0. You just check it. This you can try it as home. You will figure out many interesting solutions from this particular problem. You'll definitely figure out some interesting solution from here, and that will absolutely clear your understanding about the optimization problem. I think a single variable optimization problem. Okay. All right. So now, so far, what we have done, we have discussed the single variable optimization problem. But now let's move on to the little bit difficult part to that. Okay. So now we'll move to the multivariate optimization, unconstrained optimization problem. Okay. So when I say multivariate, I mean there are more than one variable, more than one choice variable. So remember, I started with the fact only f of x. Okay. So this is a single variable. Now I can have many variables, f of x comma y. I have 2 variables. This is 2 variable case. Let's say f of x comma y comma z is 3 var case. Okay. It could be any finite value. Let's say f of x1, x2, xn. That means the number of choice variable is n. There are n number of choice variables. Okay. For the sake of simplicity, in this particular presentation, I'll only focus on the 2 variable thing. And the idea is exactly identical to the, so in the multivariate concept, let's see whether it is 3, 4, 5, or 6, the idea is entirely identical to 2 variable things. All right. Now, identify so first again, the steps. How do I optimize this? Let's say if I have this function, let's say my f of x comma y is equal to x square plus 2y square. If this is my objective function, because this is two variables, okay, then how do I find out the optimal value of this function? Okay, so now, so if this is my objective function, the steps are exactly identical, but there is a catch. So first, the partial derivative. So now, why partial derivative? Now we have the two variable case. So first, calculate the partial derivative of the objective function with respect to the each of the decision variable. So I will have del f del x, del f del y. Why? We have used the partial derivative. Initially, see, you had a single variable, you are using the total derivative, and now we are using the partial derivative. Okay, because now we have two variable cases. I hope all of you know how to calculate the partial derivative. So, second, once we take the partial derivative, then we'll set this partial derivative equal to 0 to find out the critical point. Okay, so let's take the example of f of x comma y is equal to x square plus 2y square. Okay, all right. So again, what I have to do, I have to figure out the critical values. Okay, and yes, one thing just for this would be my suggestion to all of you. I hope all of you have using the laptop or the computer. So try and plot this curve in any. There are a lot of websites where you can plot 3D curve, right? You can plot z is equal to x square plus 2y square. You can see that how these curves are changing, right? In one variable cases, I can have this only single line, but in a multivariate case, we'll have a plane, right? So I can't show it here because otherwise we could have shown you how the curve is changing, because now we are talking about a curve, right? Over here, my derivative was changing. Let's say my x and a y, I was calculating by dx, I was calculating this is the how y is changing with respect to x, that's the slope of this curve, right? But now when you are taking multivariate case, it's a plane. In a but two variable case, a plane. So how my f is changing with respect to x while keeping y constant, because this is the idea of the partial derivative, and how my y f is changing with respect to y keeping x is constant, right? This is the idea of the partial derivative. Okay, all right. Now if I have to take the del f del x, then this is 2x, and if I take del f del y, it is 4y. All right. Now set the both the partial derivative equal to 0. Okay. Let me set this equal to 0. Then set equal to 0. Then what you will find? You will find x star is equal to 0 and y star is equal to 0. All right. So now see, I have obtained an ordered pair. Remember that these are not two critical points. These are one critical point, because now we are dealing in the, so here we are dealing on the x-axis and the y-axis. Y was giving you the functional value and x was giving you the choice variable. Okay, but now we are using the choice variable of both x and y together, which means we are operating on a Euclidean space. Okay, so now these are not two critical points, these are only one critical point. Okay, that's why you see I have this ordered pair. These are called ordered pair. I can have multiple ordered pair. Okay, or like solve the system of equations. So over here you'll have only two. So when you have the multiple things, then you can have a very complex situation. And since I am dealing with two variable cases, the system of equations, there could be multiple, again, there could be multiple critical points, but these are not two different critical points. These are one critical point. These are single critical point. Likewise, earlier it was 0, 3, 4, we obtained. Remember in the single variable cases, now instead of one number, now we have two. These are ordered pair. We are operating in a Euclidean, this is Euclidean space. In a two-dimensional Euclidean space, we are operating here, a point over here, because it's a coordinate x and coordinate x and the y. This is a point over here, point over here, point over here, point over here. So we can have this critical point when you are dealing with the two variable cases. All right. again, this critical point represent the potential solution to the optimization problem. I know that my solution will exist within these critical points. But does that mean that these are my, but I don't know which are the one where my solution is optimized or the function is optimized. I don't know, right? In order to check it further, then we have to move forward. So we have to check the another. Remember that in our one variable cases, we calculate the second order condition. All right. So over here, we'll also do the same thing. We'll classify the critical point, use the second partial derivative test of the determinant of the Hessian matrix. So now we'll bring another concept called the Hessian matrix. So what is Hessian matrix? I'll just come to classify the critical point at maxima, minima, or the saddle point, and evaluate the second partial derivative at each critical point. So don't worry, just hang on with me for a while. I'll explain it. What is Hessian matrix? Okay. So let's deal with the 2 by 2 matrices. Okay. For a function of two variables, the Hessian matrix is a two-quadruples matrix that contains the second order partial derivative. Let's denote the function as f of xy. If my objective function is f of x comma y, all right, then my first order condition that del f del x, which means my f is changing with respect to x. All right. Now del f del y, we obtain that how my f is changing with respect to y, keeping x constant. Okay, but I haven't considered the other aspects as well. What now? You remember in the second order condition, what we did in the first case, how the slope itself is changing when x is changing. That means that this would be this del square f and del x square. This shows that my f, how my slope is changing with respect to x. And this gives you, again, I have to do the same thing with f. Then how my slope of df is changing with respect to y. This slope is changing. This is d square f by dy square. Okay, but I haven't done that how this slope is changing with respect to y. So this would give you d square f by del y del x. And similarly, how my slope is changing, slope df dy is changing with respect to x, and this will give you del square f del x del y. So the compute the second order partial derivative, the del square f del x square with respect to x, del square f del y square second with respect to y, and take the derivative take the df derivative of partial derivative of df del f del x with respect to y. And then again do the same thing with this with respect to x, and these four components will give me this Hessian matrix. So earlier you remember only one thing was okay. So when we were dealing with one variable, only one second order derivative was enough. But now when you have when you were dealing with the two variable cases, one second order derivative is not enough, because remember that it's a plane. Let's say you remember, if you can see for example, you can see my hand, my palm. You say this is the surface I'm taking. If this surface is the kind of, how can I take the example? Let's say, for example, if I take this cup, if you can take this cup, you can see this cup is curved. Okay, just let me drink the water. Just look at this handle. Okay. This curve is flat. It's a curve. Okay, it's not a straight line anymore. And this is a surface. Okay, this is not a kind of a linear now. It's a surface. And if this is my x-axis and this is my y-axis, and how this slope of is changing with respect to x and the y, it is changing with respect to in all the direction, right? So imagine a kind of the top of an umbrella, a surface of an umbrella, or surface of a kind of a bowl. Okay, so we are dealing with a bowl now. So now we have to check how the slope is changing with respect to x and the y, when on the slope of del f del x is changing with respect to y. So we have to check the all possible combinations, right? When we'll be dealing with the x, y, z variable, then we'll have a 3 by 3 matrix. Okay, since that one is complicated, I'll just focus on only two things. So that's my Hessian matrix, and this will tell me whether all the critical point I have obtained here, let's say these x1, x2, x3, all these obtained here, and are these at what point my function will take the maximum or the minimum value. Okay, but this is not so straightforward. But once we have achieved this, then there are certain things. Let's say, for example, before I go into the what are the conditions, let's try and calculate how my Hessian matrix would look like. If this is my function, if xy is equal to xy, let's say it's a two variable function. So now what is your del f del x? Is y, and del f del y is x, right? Now del square f del x square is equal to 0, del square f del y square is equal to 0, and del f del square f del y del x, it would be, you just have to take the derivative with, you have to just take the del y, and this will give you this is equal to 1. Just a second. And del square f del y del x is equal to 1. Okay, so remember that how my Hessian matrix will look like. So this point is del square f del x square, this is del square f del y square, and these are all these cross things. Okay, so my Hessian matrix would look like this 0, because you see the del square f del x square, this will come here, del square f del y square, this will come here, and this is del x del y, and this will come here, and this will come here. All right, this will come here. So you can see that this is my Hessian matrix, but still we are not done. We have computed the Hessian matrix. In a two variable cases, we computed the Hessian matrix. But from here, how would I say that what are those values? Let's say if we obtain this value, then we will get y is equal to 0 and x is equal to 0. Well, at x is equal to 0, can we get the maximum or the minimum? I don't know, right? We have to check for the properties of some of the properties of the Hessian matrix. Okay, so what are the properties? So this is very important. So I am not going into detail of that. Please, if you get some time, and please read some of the books. I can recommend some of book. You can see the Sylvester Hammond second edition book. You can check that. You can think, I think Alpha Chiang. These are the standard book you can check. Okay, and why it is the case, I'm just mentioning it because we have the paucity of time. So when you have to obtain the Hessian matrix, then which critical value will give you the maximum value, or which critical point will give you the minimum value? That depends on the nature of the Hessian matrix. So how do I see that? We call it something called positive semi-definite, negative semi-definite, indefinite Hessian matrix, and semi-definite Hessian matrix. So positive definite Hessian matrix, if the Hessian matrix is positive definite, which means all the eigenvalues are positive. I hope many of you, or some of you at least, familiar with the eigenvalues. I'm not going into the details how to compute the eigenvalues or what are the eigenvalues and the eigenvectors. I'm not going into that. And if not, if you really do not recall, or maybe you have forgotten, or maybe you have not studied, I would suggest you, please pick up any mathematical economics books, and you will be easily understand the concept of the eigenvalues. If all the eigenvalues are positive, you can calculate easily. You can calculate the eigenvalues, at least in the two variable cases, and it indicates the local minima of the function of the critical point. Similarly, if the Hessian matrix is negative definite, that means all eigenvalues are negative. Eigenvalues are negative. So you have to compute the eigenvalues. You see, this process is a bit complicated, unlike the single variable cases. Okay. So then when you have all the eigenvalues are negative, then we have the local maxima. And we have the both positive and the negative values. We cannot say that all these critical point that maximum or the minimum value will be obtained. This is just a saddle point. If the functional value changes, all right. And the negative semi-definite, if the Hessian matrix is neither positive definite or nor negative definite, it is semi-definite. You just go and check it in any linear algebra book. You will find all these concepts. So, but you have to compute these eigenvalues. These are really important when you are checking, when you are dealing with the multivariate or optimization problem. All right. Okay. So, okay, these are almost same thing. I just picked up the same thing. Example to this one. Okay. Again, the profit maximization problem. If firm produces two goods, X and the Y, firm is confronted with the profit function this. Okay, and where X and Y depend on the quantity produced of two items, determine the output quantity that maximizes the profit of the firm. Again, the steps are exactly identical. What I have to do, I have to follow this thing. Take the first order condition and then set is equal to 0, and then check the second order condition at all the critical points. Okay, let's do the step-by-step thing. So this is my critical objective function, as it was already given there. Take the partial derivative dp del p del x. You can easily calculate it, 5 minus 4x, and del p del y 8 minus 6y. All right. The solve for all critical points. Setting the both partial derivative equals to 0, then you set is equal to 0 and set this equal to 0. You can calculate, let's say, x star and y star. These are I call the critical point. Is x star is equal to 5 by 4 and y star is equal to 4 by 3. At this particular point, what happens? The partial derivative are 0. This function is taking the maximum value or the minimum value. I don't know at this stage, because I'm still evaluate the second order condition at these critical points. So these are my critical points. In this particular case, I obtained only one critical points. Okay. All right. Now classify all these critical points. How do I do that? I'll calculate the Hessian matrix. Okay. So d squared dp dx squared. You just calculate d squared dp. This is dp dx. Then d squared p dx squared, which is nothing but minus 4, and d squared p dy squared. This is dp del p del y. This one. This is equal to minus 6. Okay. Now I have to also calculate the del p del y del x. This is nothing but 0, and we have to calculate del p del y like del x. This is also 0. So now I have the 4 component of the Hessian matrix. This, and this. Okay. You can see this one over here. Now, so this is my Hessian matrix. Minus 4. Pardon me for my handwriting. So it is so poor. I'm writing on iPad, so it's okay. So this is my Hessian matrix. You see, this is my Hessian matrix. And you see, if I have to calculate the eigenvalues of these two, you'll figure out the eigenvalues. Let's say lambda 1 is equal to minus 4 and lambda 2 is equal to minus 6. Okay. And this shows that since all my eigenvalues are negative, and I can have a local mixing maxima at this particular critical point. Okay. So then what firm will do? Then firm, okay, if we just look at this thing, this one, okay. And so the profit maximizing output of the firm occurs at x is equal to 5 by 4 and y is equal to 4 upon 3. Okay, therefore, to maximize the profit, the firm should produce and sell at x is equal to 5 by 4 and y is equal to y upon 3 units of the second good. Okay, so this is all about the maximization problem or the optimal optimization problem in a 2 variable cases. Now see, things are a bit complicated here. Steps are pretty exactly identical. Steps are complicated only because of the Hessian matrix, and things become even more complicated when you have 3 variables, let's say x, y, and z. Now we'll have a 3 by 3 matrix, which means there is a 9 item, 1, 2, 3, 4, 5, 6, 7, 8, 9 in a 3 by 3 cases. Okay, so Hessian matrix is even more complicated and correspondingly calculating the eigenvalues are even more difficult. Oh, no, if you have the computer and all, these are so 1 minute job, but you have to do it manually. Things are difficult. These there are many things. You can use all these chat GPTs and all to compute things. They will give you in a second. So you don't need to worry about all these things, but it is better to know how to compute the eigenvalues. It's better to read the theory first and then use any computer to calculate the eigenvalues. Okay, all right. So in a nutshell, the optimization problem in multivariable require consideration of the partial derivative and critical point in a similar manner to the single variable items. And additional techniques such as second order partial derivative test or the determinant of the Hessian matrix may be necessary for the classifications. Okay, so this is also important. So you cannot, many a time we economists sometimes overlook the second order condition, and these are not always correct. We need to be very methodical or clear what exactly we are doing. Okay, all right. I think so far, I hope I'm not going too fast, but still, I can't do anything. I'm trying to cover many things in one lecture. Okay, all right. Now, we have dealt with the unconstant optimization, both the single variable cases and the multivariable cases. So now we'll move on to the constant optimization. The constant optimization, it's clear, it is clear from the name itself. Now we have so far we haven't used any restriction on optimization. Okay. Now what we are doing, we are imposing certain restrictions. You have to operate under these restrictions. All right. So when that is the case, then we will call it a constant optimization. And in these particular cases, I particularly deal with the multivariate case, and particularly on two variable cases, because these are most of us are familiar with this kind of situation. Okay. Okay. So constant optimization refers to the process of maximizing or minimizing the function subject to certain constant or the restriction. As soon we will come with certain examples of that. What are these importance in economics? Economic constant optimization is essential for modeling real world scenario where decision maker faces limitations or the constant. Can you give me one example, the constant optimization from your day-to-day experiences? Anyone can give me any example. Then you are trying to, you are facing a constant, you have faced a constant optimization problem. Anyone can give me an example, just from the real life example. It need not to be from the mathematics. It can be from anything.
Getting maximum marks with time constraints.
Okay, getting maximum marks is time constraint. Okay, all right, that
budget
makes sense. Yeah.
Budget constraints, sir.
Budget constraints, these are directly from the economics book. So I am not asking you something directly from the economics. Maybe you have faced in your real life situation, because that will kind of that will make you kind of more.
With our limited budget, the combination of XY goods we are purchasing in the market, that we can consider it as.
Yes, yes. Maybe the day you wake up, you see in your pocket, let's say you normally you have, let's say, $100,000 in your pocket. Let's say that day it's only $500 for some reason, and immediately you're trying to figure out how much to buy of this item, that item, that item. Like you immediately start doing, as soon as you enter the market, you start doing this sort of optimization. Or maybe you think of, let's say, until in many rural areas we face a situation. Student education, let's say, because in the current scenario, parents are spending a lot more on student education, but at the same time, because their budget is limited, because their income is limited, then how much they want to invest on student education, or maybe their daughter's education, and how much to invest on consume on certain product. Let's say, for example, there are household having a lot of consumption of sin good. Sin good means, let's say, consumption of tobacco, alcohol, or maybe this kind of product, right? So how kind of families and household are optimizing their, are allocating their resources. When there is a budget constraint, allocating their resources on two types of items. So these are the real life example. Okay, for example, we buy apple and the oranges, you have $100 in the market. These are easy example we use in our day-to-day life. But these are the real life example, or maybe economists who are trying to solve all these things. You know how much household are trying to allocate the resources on different components depending on budget constraint. This is a budget constraint. Let's say somebody, I think Arvind just said, is the time constant. I have 24 hours time, and then out of 24 hours, how much I can allocate, how much I can work, how much I can use for the leisure, and how much I can invest to help my daughter for their homework. Okay, so there's a three component thing. Now you see that these are the real life problems we economists or maybe all the policymakers are trying to solve. And many of you can go back to your home and try and see then how you are managing it. You see your budget and how much you're investing on your son's education and or your daughter's education, or how much you're investing on some durable goods or something. Well, so these are the kind of real life examples where we economists are dealing on day-to-day basis. Okay, all right. Again, so how do I see that? Then again, you have to figure out the objective function. This always remains the same, and also our decision variable. So decision variable, how do I allocate? Let's say there is a resource allocation problem between two goods. So there are, so my objective now, so now my objective function is f of x, y. X is the one good and y is the another good, right? So that my decision variables are x and the y. Let's say if I am the household name, I am trying to allocate the resources on 4 items. Then I have 4 choice variables, right? Let's say consumption on vegetable, consumption of pulses, consumption of education, and consumption of durable goods, like this. Okay, all right. Now maximize and so now we can maximize or minimize these things. Now I have using a constant. Constant means, let's say this is a budget constant. Okay. For example, I want to maximize the utility. Let's say f of x is equal to my utility function x to the power alpha and y to the power beta, and I have the budget constant p of x plus p of y is equal to, let's say, m. X is the px is the price of item x and y is the price of item y, and m is the total income. And this could be, my income could be less than equal to, okay, or this is the concept of the equality. Let's say this is equality. In this entire presentation, I'll be only dealing with the equality thing. Okay, and inequality things are even more complicated. Again, you can always go back once you have this idea of the equality thing. Inequality thing is the more general version. Then let's say you can say that x1 is greater than equals to 0, or y is greater than strictly greater than 0. So these are my inequality constants. Okay, so maximizing profit for a firm subject to production constant or the budget constant. Maximizing utility for a consumer. Let's say, for example, this example I have taken. So these all are the definition of the constant optimization. So example of the constant optimization. So how do I solve it? Okay, so one way of doing is to substitution method. So that I will discuss later. But there are different ways to solve, but we will focus on the Lagrange multiplier method. When you are dealing with the constant optimization problem, so we will deal with the Lagrange multiplier techniques. So what is Lagrange multiplier? To introduce a Lagrange multiplier to incorporate. So Lagrange multiplier, what it does is introduce a Lagrange multiplier to incorporate the constant into the objective function. So remember that when I was dealing with, let's say, 12x minus 2x square, this case, this f of x, we started with this example, right? So this is a single variable, there is no constant. But now I have a constant. How to deal with the constant? To deal with this constant, to incorporate that constant into my objective function, I use a multiplier called Lagrange multiplier. To formulate the Lagrange multiplier, what I do, let's say f of x minus lambda is your Lagrange multiplier, and you write gx minus c. Okay, let's say P of x plus P of y is equal to m, let's say. Okay, let's say this is your g of x comma y, and then you like g of x comma y minus m, set is equal to 0, and then you add another variable lambda, which is called the Lagrange multiplier, and we have the Lagrangian function now. Now the Lagrangian function is a function of your choice variable and the new introduced variable, which is the Lagrange multiplier. Okay, and then we'll just come how do I solve it. Then another is about the Kuntakar condition. So when you use the both equality and the inequality condition, so here we are dealing with the equality condition, and in this case it is a more general condition, the equal and the unequal condition. Likewise, this both will be there in my optimization process. Then we'll use the Kuntakar condition. So in today's presentation, I won't be dealing with this. Okay, for this requires further discussion, further elaborate discussion to discuss on the Kuntakar condition and the numerical methods, the Newton's methods. I am not going into that today. Now let's focus on the Lagrange multiplier methods. Okay, so again, I have to figure out my objective function f of xy and my constant g of xy is equal to 0. And we want to minimize f of xy subject to this. Okay, so let's to give one example. Let's say my f of xy, x to the power alpha and y to the power beta, and my g of xy is equal to px minus p of y minus m is equal to 0. Right? This is my constant. This is my budget constant. This is my utility. Mainly, I think these are all familiar to you from your introductory micro 101. These are pretty familiar. So this is the structure of a constant optimization. Okay. Now I will set the Lagrangian. So what I'll do, I'll introduce a Lagrange multiplier. That is lambda. So this is my Lagrangian function lambda L. These are my x and y are my choice variables, right? And now I'm introducing a new variable lambda. Now L becomes a function of three variables x, y, and lambda. And this is my f of xy minus lambda gxy. So this is my gx. Okay. And where lambda is the Lagrange multiplier. Okay, so I think many of you have done this thing. They are familiar with this Lagrange multiplier. If you are not, please bear with me for a while. So these are the new variable we have introduced into the system just to incorporate the g of xy, because these are my constant. These are my restriction now which I am facing. Now again, everything is now when you have this L of xy, now everything is identical. Likewise, we have done with the multivariate cases, multivariate unconstant optimization. This is now my unconstant thing. So far, this was my constant optimization, objective function and the constant. Now I have brought them together in a single function, and this has now has become my unconstant. Right? Now we do not have any constant. Then what? Now the unconstant optimization with three variables now. Now you see, I have three variables now: x, y, and lambda. This is my unconstant optimization with three variables now. That's it, nothing else. Okay. So now once I know that this is my unconstant optimization with three variables, then I know all these steps. One is I have to figure out the critical value. Then in order to do that, I have to figure out the first order condition. That means I have to this is my function. I have to function del n by del x. I have to calculate del L by del y. Then since it's a three variable things, I have to calculate del L well, del lambda. These three I need to calculate. All right. Okay. And then we'll set this equal to 0. Then you have to form this is nabla L. So this sign is called nabla. Okay. So don't worry. So we are writing the kind of column vector form. del L, del X, del L, del Y, del L, del lambda. This is exactly what I have done. What you will do? So what you will get? If you calculate del L, del X, what you will get? You will get A prime X, what else? Del F, del X minus lambda del G del X, right? If you do this, what you will get? Del F del Y minus lambda del G del Y. And if you do this thing, because this is if you calculate del L del lambda, because this is free form, this f of x y free form lambda, only thing you will have, this you will have minus G of x comma y, right? And this is exactly what you have it here. Right? And then you will set this equal to 0, because I have to set all the first order condition equal to 0. Because what I have to find out, I have to find all these critical points. So now my critical points are in this form: x star, y star, and the lambda star. This triplet, right? So now, when you solve the first order condition, so you will set this equal to 0 to solve for the first order condition. You will get all these x star, y star, and the lambda. You will get a bunch of these things, and you have to figure out the solution of. Now, the second order condition. You remember what I said at the beginning? If the second order, if your unconstant optimization is of 3 variables, let's say f of x, y, and z, then your Hessian matrix would be a 3 by 3 square matrix, right? So it is something like that. There will be variable 1, 2, 3, 4, 5, 6, 7, 8, and 9. There will be 9 entries into the Hessian matrix over this. When you compute the Hessian matrix from this, and this is my now unconstant optimization with the Lagrangian function is my unconstant optimization. So correspondingly, I will have Hessian matrix is a 3 by 3, 3 cross 3 Hessian matrix, and the rest of the steps are exactly identical. So I have to figure out all this. So this my Hessian matrix will look like this. All right. So this is my Hessian matrix. You see, there are 9 entries out of that. We compute the border Hessian matrix, and analyze the sign, the determine the nature of the critical point. So the nature of the critical point, remember the condition I specified, all these eigenvalues are negative, then will get that will give you the maximum value, eigenvalues are positive, that will give you the minimum value of your objective function. That remains the same here. All right. Okay. So this is the kind of fundamental idea of constant optimization. Now let's try and solve one particular problem. Okay, let's maximize the Cobb-Douglas utility function. This is the kind of example I was giving. Let's say x to the power half and y to the power half subject to the budget constant this. Let's say x is apple, y is orange. Okay, then what are these x star and the y stars? Okay, set the Lagrangian. You just set the Lagrangian like this. This is exactly what I've said. This is your gx comma y. This is your f of x comma y, and take the first order condition. That's it, del L, del X. Because now you are not taking any derivative with respect to del F, del X, del G, del X. It is del L, del X, because L is your Lagrangian function now. So this is your first order condition. Second, this is your third first order condition. So solving this equation will give you the x, y, and the lambda. If you solve this first order condition, the system of equation, you get x star is equal to 20, y star is equal to 10, and lambda star is equal to 1 upon 20. All right. Now I have to evaluate all these points, because this is my critical point. I don't know that my maximum value, other the function, other the utility will be optimized or maximized or not at this particular point. I have to check the second order condition. So I will compute the border region matrix, and if you compute the border region matrix, this will look like this. Okay, And remember that all these x's and y's, we have obtained that these x's and this y, this x, y, and lambda you have obtained. You plug in this value in this Hessian matrix. Once you figure out all these factors, then your determinant is giving in these things, and all you can calculate this your I would say eigenvalue values 1, 2, and 3, and you calculate all these values are negative. In this case, you will find out it's a negative, and therefore from this case, from there you can conclude that these are indeed gives you maximum utility at this particular point. Okay, so this is one example from the of your utility exam utility maximization problem. If I take the another problem from the, let's say, cost minimization, I think this is a problem I started with, x square plus 2y square. Again, do the same thing. This is my objective function. Okay, now, okay. So, all right. Okay, this ends the constant optimization with example. Okay, so now I'll discuss few random examples. Okay, from both the constant and the, particularly with the multivariate thing, from the unconstant optimization, the constant optimization. I have, I think, 10 minutes. I'll just quickly do, and if you have any question, I'll just open the floor to all of you. Okay, if this is your optimization, this is your function, then how, what's the kind of, what are the values of x and y, the cost is minimized. Again, you do the same thing. Take the first order conditions and also calculate the critical values, and then check the second order conditions, compute the Hessian matrix, and this Hessian matrix, indicates a local minima, because all your eigenvalues are positive, it gives you the local minima. Another, the profit maximization problem. I think you can note down the problem, you can solve it on your own the same way. 20x minus 2x square, you can pick up your own example if you want. Because these are the solved example, I don't want to solve. Okay, let's take the another example. Again, the same thing, another profit maximization problem. You can solve it if you are interested. I thought I'll get time, I'll show it to here, but I don't have time. So these are step by step. If you need this slide, I can share. Okay, I think many of you have done the steady state slope solo growth model. If you are interested, if you have done this thing, please, I would suggest you or urge all of you to go back and check to check the existence of the optimization problem in the solo growth model, in a particular in the steady state. So this is what I thought I'll show, but I don't have time to do that. Okay, now just very fundamental but very important thing. Okay, just what does this function fx which is minimum value? Can anyone tell me f of x where it takes the minimum value? You can, from the clearly, this is the f of x square, this red card. You can clearly say that x is equal to 0, the function takes the minimum value. All right, but how do I make sure that it is this? You just have to take f prime x is equal to 2x, it's equal to 0, x is equal to 0, and f double prime x is equal to 2, which is less than 0. That tells you that at x is equal to 0, the function takes the minimum value. Okay, all right. But how about this? F of x is equal to x cube. Is it still true for x is equal to 3, x is equal to 0? Is it still true for the x is equal to 0? Because you see that x is equal to 0, the function value is 0. And this is f of x is equal to x cube. Again, let's check that f of x is equal to x cube, then f prime x is equal to 3x square, and you set it equal to 0, then x is equal to 0, f double prime x is equal to 6x. And at x is equal to 0, it is 0. You remember that x is equal to 0, that is inconclusive. It is neither maximum nor minimum at x is equal to 0. Okay? And how about this function? F of x cubed minus 6x squared plus 9x. You can see that this function, it takes the value, maximum value at here and minimum value at here, right? And if you exactly follow the same value, at one case at x is equal to 1, at f double prime x is equal to 1, you will get is less than 0, and if double prime x is equal to 3, you will find x greater than 0. You will exactly find it if you follow the all these steps which I've just mentioned. Okay, but you always see that is this the maximum? The maximum value is obtained here, isn't it? If I go further over here, it's even more maximum. If I go down here, we can have even lower value, isn't it? And why we are considering that these are the maximum value and these are the minimum value.
So that is -3 is f0 to x.
No, so when I taking the functional value, which means I'm talking the value when the function takes the maximum value. Here it takes the maximum value, but it also the function value of this function, the red line, is greater than this particular point. But I'm still saying at this particular point, this function is taking the maximum value, and this particular point, this function will make minimum value, and not here. When okay, so when you are saying these things, we are talking about the local maxima or the local minima. So in the entire presentation, what I have discussed is talks about the existence of the local minima of the local maxima. In order to, so if something obtained here, or maybe something is there, okay, so then we, in that case, in order to do that existence of the global maxima or the global minima, we have to go for further level of discussion. Am I audible now? Can you hear me? Yeah. Okay.
Yes, sir, yes.
Okay. I think there is some problem with the phone charger. I have to. So this is all what I plan for this today's presentation. I hope this will help you at least a bit, or will encourage at least some of you to go back and check and to apply some of the concepts in your micro or macro 101 lecture. And I tried to keep the presentation as simple as possible to keep this presentation away from all these typical mathematical jargons and notations and all. I tried to keep it as simple as possible, and I hope this will help you.
Sir, for this example, that is f0 x.
If you have any question, you can ask me now. Yes, can you talk a little loud?
So for this example 3.
Yes.
The I mean, which you are showing, that is f0 x is -3. So how can you substantiate this? That is the minimum value.
So the minimum value is obtained at x is equal to 3. If you just calculate the f prime x, what you will get? You will get.
So -3, sir, -3.
No, I think you will get x is equal to 3, and x is equal to 3 and x is equal to 1. Or maybe x equal also 3x square minus 12x plus 9, you get x square minus 4x plus 9. No, sorry, 3, that
No,
means
sir.
x minus 1 and x minus 3. I think critical value was obtained at x is equal to 1 and x is equal to 3, not minus 3. Okay. If you have any question, you can ask me, please.
Sir, is there any way we can draw the unconstrained optimization?
Can you talk little loud? I can't hear you.
Sir, is there any, you have, the graphs are very clear with regarding to the unconstrained optimization.
Just give me a second. Just give me a second. Yes, tell me.
The graphs of unconstrained optimization are very clear, sir. When it comes to the constrained optimization, how can we, represent the same through a graph? If we have to present this through a graph?
No, see the unconstrained optimization thing. For example, I can draw it for the utility maximization cases. For example, this thing. Let's say this is your budget constant. Okay, these are your utility function. So at here it is optimized.
Okay.
Right. So this is, but the thing is that this is actually not the single line. So because when you plot the f of xy, let's say, so this is a plane you will generate in a plane you will generate in a plane, three-dimensional plane. So it's not always possible to kind of visualize in three-dimensional cases, or maybe in this case it is pretty easy to visualize. In a two variable cases, when you have a constant and you have the objective function, you can do it. It's not a big problem because objective function basically, what are these things? These are the line, all these possible values of x and y. Let's say if I have to take these things, let's say these are the utility function, right? Let's say this is I1, I2, I3. All these values of x and y, this utility remain constant. Utility remain constant over here, right? But when you have the budget constant, you are going like, let's say, let me take a different color. Let's say you are going like this, because if you have to consume this budget, your utility will be maximized. But over here, if you take this option, utility is maximized, right? This is standard kind of utility maximization problem from the microeconomic stuff. So I'm not doing anything new, but my idea of the entire presentation is to, like, let's say sometimes you are unable to visualize the stuff. Let's say you have the three variable things or the three variable thing. Let's say household optimization problem, household resource allocation problem in an actual research scenario. For example, you are doing some economic research and or you want to see that how household allocate resources when they have the fixed income between the consumption of vegetable, consumption of protein items, and the education of the student education. Okay, and they have the, let's say, Cobb-Douglas type of the CS utility function with the three component. Then it's not so easy every single time to visualize using curve. Then you have to just follow the mathematical techniques to solve for this X star, Y star, and Z star to solve. But I would still always recommend all of you, like, try and draw some curve that will help you to understand what exactly I am doing. Mathematically, if you are trying to solve some problem, which gives you some kind of some mechanical ways to understand the problem, right? But in order to actually what we are doing, what exactly happening, unless we can't visualize it, that is, for me, like, it's not like, we are eating it but not digesting it, something like that. So that's my kind of
Okay, thank you very much, sir. I think
and
you have delivered a great lecture on optimization. I think this is by far best sessions we had online. And if you have time, if you can give us time, I think we would love to have you more sessions in the coming future, sir. And on behalf of all the faculty and CC and myself, I extend my heartfelt gratitude and thanks to you, sir. Thank you, sir. Thank you very much.
Thank you, Arvind. Thank you so much for inviting me for the lecture. I really enjoyed these things. I'm grateful that you gave me this opportunity to deliver a lecture in front of the distinguished faculty members, and which are, I guess many of them are pretty senior to me. I'm very new to this academics. I just started teaching at Delhi School of Economics in last 3.5 years. And also this is even a learning process. I'm still learning, how to teach students and make the concept, how easily I can deliver some of the difficult mathematical concepts. And thank you, Arvind, for giving me this opportunity. And of course, I'll be available if you call me for some talk or something. I'll try to manage some time
Sir,
from
can
my
you
schedule.
Sir, can you mention your mail ID, sir? Mail ID.
Yeah, I think this is with Arvind. Arvind, you can please share with them if you have any doubts or something, and if you want me to share the slide, I can share with Arvind. Arvind, is that okay?
Yes, sir. Yes, sir. I'll share the mail, and if you can forward the PPT. I think the PPT itself is, it's like self-learning material. It's very well made, sir. If you can share the PPT, it will be very helpful for us, sir.
Yes. I'll do that. And when somebody asks for my email ID, I think, ma'am, you can take it from Arvind. It is, you can note it down. It's sandeep@econdcu.org, or maybe you can go to Delhi School of Economics website. You can find my email IDs. You can drop me an email any point of time. Not only to discuss mathematics, I am always open to discuss any of the economics research. I am particularly working on healthcare and education, and some of the political economics I'm working. If you are really interested to discuss some topic, or maybe whatever you want to discuss, I'm completely I'll be always available. If not
Thank you so
immediately,
much, sir. Thank you so much, sir, for making interesting session. Thank you so much.
Thank you for giving me the opportunity. Thank you, Arvind. So, may I leave this session now, or?
Yes, sir. Yes, sir. Thank you very much, sir.
Okay. And I think it's a big round of applause to all the participants who listen, who was listening to me so patiently. Thank you so much. Thank you, everyone. Thank you. Bye.
Thank you.